Tonight, we're going to explore how long it would actually take humanity to travel 1 light year. It sounds like a modest beginning. A single light year, the first clean milestone on the road between our solar system and the stars beyond it. But if a spacecraft left Earth in 2026 and traveled outward at roughly the speed of Voyager 1, it would not cross that distance during our lifetime. It would not cross it during the lifetime of our civilization as we know it. It would finally reach 1 light year from the solar system, sometime around the year 19,661. By the end of tonight, you're going to understand why one of the smallest distances commonly discussed in astronomy may still demand technology, energy, and endurance far beyond anything humanity has ever built. A light year is approximately 9.46 trillion kilometers. That is the distance light covers during 1 year, while moving at about 300,000 kilometers every second. Voyager 1, the most distant human-made object in existence, is escaping from the solar system at approximately 17 kilometers per second relative to the Sun. That is fast enough to cross the entire width of the continental United States in only a few minutes. It is fast enough to travel more than 1.4 million kilometers in a single day. And because almost nothing in interstellar space produces meaningful drag, Voyager can continue coasting at roughly that speed for thousands of years. Given that kind of motion, 1 light year might seem manageable. The spacecraft is already moving between the stars. Its engines do not need to burn continuously. Its momentum can carry it onward long after its power supply fails and its final radio signal disappears. Yet at 17 kilometers per second, traveling 1 light year would still take approximately 17,635 years. A machine departing in 2026 would cross the boundary only after more than 3 times the entire length of recorded human history had passed. The number is so large that the calendar begins to feel less like a schedule and more like a different world. The people who launched the spacecraft would be gone. Their languages could be gone. The nations that approved the mission, the organizations that tracked it, and the computers that calculated its path could survive only through many layers of replacement and reinvention. Even the northern sky would have changed. Earth's axis slowly shifts direction through a cycle, lasting roughly 26,000 years. By the time a Voyager speed spacecraft completed 1 light year, Polaris would no longer occupy the same familiar place above the North Pole. And this is only the first light year. The nearest star beyond the Sun is more than 4 light years away. The Milky Way stretches across roughly 100,000 light years. The first milestone is a tiny fraction of the galaxy. Yet with present spacecraft speeds, it already extends almost 18,000 years into the future. That is the contradiction at the center of tonight's journey. A light year is treated as one of astronomy's smaller units. We use it to describe nearby stars, local clouds of gas, and the immediate neighborhood surrounding the solar system. Compared with the size of the galaxy, 1 light year is almost nothing. Compared with the distances humanity has physically traveled, it is enormous. Before we continue, if you enjoy calm journeys through the deeper realities of space, take a moment to like the video or subscribe. It is a small action, but it helps this channel reach more people who enjoy exploring these questions slowly and carefully. Now, let's begin with the spacecraft itself. Imagine a vehicle leaving Earth in 2026. Its launch vehicle carries it through the atmosphere and places it on a path away from our planet. Additional propulsion sends it beyond the Moon, past Mars, and eventually through the region of the giant planets. Perhaps it passes Jupiter and uses the planet's gravity to gain more speed. Perhaps it follows a carefully designed path near the inner solar system before turning permanently outward. Eventually, its engines stop. The fuel is conserved or exhausted. The spacecraft enters the long coasting phase that will occupy nearly all of its journey. Behind it, Earth continues traveling around the Sun. The planets continue following their orbits. The entire solar system continues moving through the Milky Way. The spacecraft and its point of origin are both in motion, slowly separating as they follow slightly different paths through the galaxy. There is no destination planet waiting at the end. There is no nearby star marking the boundary. The mission is aimed at a distance itself. Somewhere far ahead is an imaginary sphere surrounding the solar system. Every point on that sphere lies exactly 1 light-year from its center. The spacecraft must simply continue moving until its distance from home reaches 9.46 trillion kilometers. Nothing physical waits there. No wall separates the space before it from the space after it. There is no flash of light, no sudden change in gravity, and no instrument alarm announcing that the crossing has occurred. The boundary exists because an observer measures the spacecraft's position and calculates that 1 complete light-year now lies between the vehicle and the place it left behind. That measurement sounds simple, but even the phrase, "the place it left behind," creates a problem. Should the distance be measured from Earth? Should it be measured from the center of the Sun? Should it be measured from the solar system's location in 2026? Even though the Sun itself will move through the galaxy during the journey? And what kind of spacecraft are we measuring? A machine similar to Voyager 1 produces an arrival year deep in the future. A spacecraft, somehow maintaining Parker Solar Probe's record speed, would still need more than 1,500 years. A far more advanced probe traveling at 1% of light speed would arrive 100 years after launch. At 10%, the crossing would take about 10 years. At 20%, it would take only 5. Under an idealized form of continuous acceleration that no known engine can provide, the journey could fall below 2 years. Every answer is based on the same distance. What changes is the machine attempting to cross it. Its propulsion determines its speed. Its mass determines how much energy must be supplied. Its shielding determines whether it survives the journey. Its power source determines whether it remains awake when it arrives. And its communication system determines when Earth finally learns that the crossing has happened. Before any of those technologies can be compared, the distance itself needs to become clear. A light year contains the word year, but it is not a measure of time. It is what happens when the fastest thing in the universe is allowed to travel without interruption for an entire year. And once that year is turned into distance, the true size of the journey begins to appear. The word year is what makes this unit feel familiar. On Earth, a year describes time. It marks 1 complete orbit of our planet around the Sun, lasting a little more than 365 days. A light year is built from that same span of time, but the final unit describes distance. It measures how far light travels while Earth completes 1 orbit. That definition begins with the speed of light. In empty space, light moves at approximately 300,000 kilometers every second. The more precise figure is about 299,792 kilometers per second, though 300,000 is accurate enough for most travel estimates. During a single second, light could travel around Earth more than 7 times. Earth's circumference around the equator is roughly 40,000 kilometers. By the time 1 second has passed, a beam of light has already covered nearly 300,000 kilometers. After 1 minute, it has traveled approximately 18 million kilometers. That is almost half the average distance between Earth and Mars when the 2 planets happen to be relatively close. The exact separation between Earth and Mars changes constantly because both planets follow different orbits around the Sun. At some points, they come within roughly 55 million kilometers of each other. At other times, more than 400 million kilometers separates them. Light crosses 18 million kilometers in 1 minute, regardless of where the planets happen to be. After 1 hour, The distance reaches approximately 1.08 billion kilometers. That is enough to pass the orbit of Jupiter under some arrangements of the planets, though a real spacecraft could not follow such a perfectly direct route through a moving solar system. A full day carries light much farther. 24 hours contain 86,400 seconds. During that time, light travels about 25.9 billion kilometers. That distance is called one light day. Voyager 1 will reach approximately that separation from Earth in November of 2026, after nearly 49 years of travel. Light covers the same distance in one day. The comparison shows why the word light matters as much as the word year. The unit is built around the fastest known motion in nature. Nothing carrying information or matter has ever been observed moving through empty space faster than light. When light travels for an entire year, the result is approximately 9.46 trillion kilometers. In miles, the same distance is about 5.88 trillion. Those values are difficult to picture because ordinary travel rarely uses numbers that large. Even distances between planets are usually measured in millions or billions of kilometers. A light year pushes the scale into trillions. The number comes from a straightforward calculation. Start with roughly 300,000 kilometers each second. Multiply by 60 seconds in a minute. Continue through 60 minutes in an hour, 24 hours in a day, and slightly more than 365 days in a year. Each step extends the same beam farther along its path. The speed stays constant in a vacuum. Elapsed time determines the distance reached. This is why one light year contains no built-in promise about how long a spacecraft will need to cross it. Light takes 1 year because light moves at light speed. Voyager 1 moves at only a tiny fraction of that velocity. At approximately 17 kilometers per second, it covers about 1.47 million kilometers each day. That sounds enormous until it is placed beside the 25.9 billion kilometers light covers during the same day. Light travels roughly 17,600 times faster than Voyager 1. The travel time grows by the same factor. 1 year for light becomes more than 17,000 years for a Voyager speed spacecraft. The distance has not changed. Only the speed of the traveler has changed. Astronomers often use another unit to describe distances inside a planetary system. It is called the astronomical unit. 1 astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers. Earth's orbit is slightly oval, so the exact separation changes during the year. The average provides a convenient standard. Earth sits about 1 astronomical unit from the Sun. Mars orbits at an average distance of roughly 1.5 astronomical units. Jupiter lies about 5.2 astronomical units away. Neptune circles at approximately 30 astronomical units. Voyager 1 has traveled beyond 160 astronomical units from the Sunday. Those figures make the outer planets and distant spacecraft easier to compare without repeating enormous kilometer values. The same method can be applied to a light year. Divide 9.46 trillion kilometers by approximately 150 million kilometers. The result is about 63,241 astronomical units. A spacecraft leaving the region near Earth would need to cross the equivalent of more than 63,000 Earth-to-Sun distances before completing 1 light year. Neptune's orbit reaches only about 30 astronomical units from the Sun. The heliopause crossed by Voyager 1 lies near 121 astronomical units in its direction of travel. 1 light year extends more than 500 times farther than that crossing point. This conversion will matter later because the solar system does not end neatly at Neptune or even at the heliopause. Far beyond the planets lies a proposed population of distant icy objects known as the Oort Cloud. Some estimates place its outer reaches tens of thousands of astronomical units from the Sun. possibly far enough to overlap the 1 light-year milestone. The distance can now be stated clearly. It is approximately 9.46 trillion kilometers. It is about 5.88 trillion miles. It is roughly 63,241 astronomical units. None of those measurements creates a physical landmark in space. A spacecraft would continue through the same darkness before and after the crossing. Determining when it has traveled 1 light-year requires choosing the exact point from which that distance will be measured. Those 63,241 astronomical units can be pictured as the radius of an enormous invisible sphere. Place the Sun at its center. Measure 1 light-year outward in every direction. Every point reached by that measurement belongs to the same imagined surface. A spacecraft crossing through any part of it has traveled 1 light-year from the chosen center. The bright line, sometimes shown in illustrations or thumbnails, is only a visual guide. Space contains no wall at that distance. No beacon waits there. No natural field suddenly switches on as the spacecraft passes through. Its instruments may record exactly the same surrounding gas, dust, radiation, and magnetic conditions 1 moment before the crossing and 1 moment afterward. Only the measured separation has changed. That makes the center of the sphere important. Distance always describes the separation between 2 defined positions. A journey of 1 light-year, therefore, needs a starting reference point that remains clear throughout the calculation. Earth provides the most familiar option. The mission begins there, so the launch site could be treated as the center. A spacecraft leaving from Florida, French Guiana, or another launch location starts from a specific point on Earth's rotating surface. Within hours, however, that launch site has turned away from its original position. Earth completes 1 rotation in approximately 24 hours. The planet also continues along its orbit, covering nearly 30 kilometers around the Sun every second. After 6 months, Earth has moved to roughly the opposite side of that orbit. The starting planet never remains where the spacecraft left it. Astronomers could instead preserve Earth's exact position at the moment of launch as a fixed coordinate. That approach creates a sphere centered on a point in space that Earth immediately leaves behind. The spacecraft would eventually cross 1 light-year from that original location, even though the planet itself had traveled far away. Such a calculation is possible, but it does not describe the craft's continuing separation from its home system especially well. Using the Sun as the center produces a more useful standard. Earth orbits at an average distance of 1 astronomical unit, approximately 150 million kilometers. Light needs about 8 minutes and 20 seconds to travel from the Sun to Earth. The difference between measuring from Earth and measuring from the Sun is therefore a little more than 8 light minutes at most, when comparing their positions at a given moment. Against a distance of 1 full light-year, that offset is small. 1 year contains more than 500,000 minutes. Shifting the center by 8 light minutes changes the total by only a tiny fraction. Scientific measurements can still depend on tiny fractions, especially when exact arrival times are being calculated. For this journey, Sun relative distance gives the clearest and most consistent result. The spacecraft begins near the Sun, receives the speed needed to escape its gravity, and then increases its separation from the center of the solar system. When that separation reaches approximately 9.46 trillion kilometers, it has completed 1 light-year under the standard used throughout this journey. Even this definition contains motion. The Sun does not occupy a permanent location in space. It travels around the center of the Milky Way at roughly 230 kilometers per second. 1 complete galactic orbit takes about 230 million years. During a Voyager speed journey lasting more than 17,000 years, the Sun would move roughly 13 light-years along its path around the galaxy. That does not place the spacecraft 13 light-years away from the Sun. Both objects begin with the same broad galactic motion. The spacecraft inherits the velocity of Earth and the solar system when it launches. Its escape speed is added to that shared motion, producing a gradual separation between two objects that continue traveling through the galaxy together. An observer outside the Milky Way would see the Sun and spacecraft following curved paths around the galactic center. Their trajectories would remain close at first and slowly diverge. From the Sun's moving point of view, the spacecraft simply continues outward. This is a reference frame. A reference frame is the chosen viewpoint from which position and motion are measured. Passengers sitting inside a smooth aircraft may describe themselves as motionless relative to their seats. Someone standing on the ground describes the same passengers as moving hundreds of kilometers per hour. Both descriptions can be correct because each uses a different reference frame. Interstellar travel requires the same care. A spacecraft can be 1 light-year from the Sun, while both are moving rapidly around the Milky Way. It can also be 1 light-year from the Sun's future position, while lying more than 1 light-year from the place where the Sun was located at launch. The title milestone refers to the growing separation between the departing craft and the moving center of its home system. Mission computers would determine that separation through repeated position and velocity measurements. Radio signals from Earth could measure distance through their travel time. Doppler shifts could reveal whether the spacecraft was moving toward or away from a receiving station and how quickly that motion was changing. Observations of stars and pulsars could eventually help the craft determine its own position without waiting for instructions from Earth. When the calculated distance finally reaches 1 light-year, nothing outside the spacecraft needs to respond. The crossing exists in navigation data. A number changes from slightly below 1 light-year to slightly above it. The craft continues traveling along the same path, unaware that an invisible human-defined surface has just fallen behind. A far smaller version of this kind of milestone is approaching in the real solar system. Voyager 1 has been increasing its distance from Earth since September of 1977. During November of 2026, that separation will become large enough that light itself needs an entire day to cross it. Voyager 1 began this journey long before anyone knew whether a spacecraft could remain active for half a century. It left Cape Canaveral, Florida, on September 5, 1977. A Titan IIIe Centaur rocket carried the probe away from Earth and placed it on a fast path toward Jupiter. The spacecraft weighed about 825 kilograms at launch. Its main communication dish measured 3.7 meters across. 3 radioisotope generators supplied its electricity by converting heat from slowly decaying plutonium into electrical power. The original planetary mission was expected to last about 5 years. Voyager would visit Jupiter, continue toward Saturn, return its measurements, and gradually fade as its power declined. That compact mission became the longest continuous spacecraft journey ever attempted. Voyager 1 reached Jupiter in March of 1979. The giant planet's gravity curved the spacecraft's path and increased its speed relative to the Sun. Cameras aboard the probe recorded active volcanoes on Jupiter's moon Io, the first active volcanoes discovered anywhere beyond Earth. The spacecraft continued towards Saturn and arrived there in November of 1980. Its close encounter with Saturn's moon Titan changed the direction of its flight. Voyager left the planetary region on a path tilted above the broad plane in which most planets orbit. There would be no later visit to Uranus or Neptune. Its route now pointed permanently outward. The spacecraft continued beyond Saturn, while the planet slowly became another bright point behind it. Voyager passed the orbit of Uranus without approaching the planet. It crossed Neptune's orbital distance and entered regions that no functioning spacecraft had previously explored. In February of 1990, its cameras took a final series of images looking back toward the planets. One of those photographs showed Earth as a tiny point of light from approximately 6 billion kilometers away. The cameras were then switched off to conserve electrical power and computer resources. Voyager continued traveling without them. The surrounding solar wind gradually weakened as the spacecraft moved farther from the Sun. This wind is a thin stream of charged particles flowing outward from the solar atmosphere. It fills an enormous region called the heliosphere. The heliosphere surrounds the planets and shields them from part of the high-energy radiation arriving from the galaxy. Voyager 1 crossed the heliopause on August 25, 2012. The heliopause is the outer boundary where the outward pressure of the solar wind gives way to the pressure of the interstellar material surrounding the solar system. The crossing occurred about 121 astronomical units from the Sun. Voyager had become the first human-made object known to enter interstellar space while still operating. Its journey had lasted almost 35 years. Even then, the spacecraft remained only a small fraction of 1 light-year from home. Voyager continued outward at approximately 17 kilometers per second relative to the Sun. During each hour, it traveled more than 60,000 kilometers. During each day, it added roughly 1.47 million kilometers to its path. Year after year, that steady motion widened the separation between the probe and Earth. The growing distance can be expressed in kilometers or astronomical units. It can also be expressed through the time required for light to cross it. Radio signals travel at the speed of light. When mission controllers send a command, the signal begins moving through space at almost 300,000 kilometers per second. Voyager has already traveled so far that this command now requires almost a full day to reach the spacecraft. NASA calculates that on November 18, 2026, Voyager 1 will be 1 light day from Earth. Its distance will be approximately 25.9 billion kilometers. In miles, that is about 16.1 billion. A radio signal leaving Earth on that date will need 24 hours to arrive. Any response transmitted immediately by Voyager will require another 24 hours to return. The round trip will take 2 full days, even before the spacecraft has spent time receiving the command and preparing its reply. 1 light day is an extraordinary human achievement. No other machine built on Earth has traveled that far from the people who constructed it. The probe will reach this milestone almost 49 years after launch. Many of the engineers who designed its instruments began their work during the 1960s and early 1970s. The spacecraft still carries computers created before modern personal computers became common. Its memory is tiny by current standards. Yet those systems have continued processing commands across billions of kilometers. The milestone also reveals how much farther 1 light year extends. A year contains roughly 365 days. 1 light day is therefore about 1 part in 365 of a light year. Voyager's separation on November 18th will represent approximately 0.27% of that larger distance. Almost half a century of continuous travel will have completed less than 1/3 of 1%. At the same speed, the remaining distance would require more than 17,000 additional years. Light covers Voyager's entire 49-year path in a single day. It would cover the full tidal distance in 1 year. The spacecraft needs thousands of human lifetimes to complete the same route. Voyager 1 provides the clearest real example because it is the most distant spacecraft humanity has built. Its position does not mean it began with the fastest launch ever achieved. Its continuing escape speed also differs from the brief record speeds reached by spacecraft moving through powerful gravitational fields. The most distant machine, the fastest object at launch, and the fastest human-made object are 3 different records. Understanding why requires looking more carefully at how spacecraft speed is measured. Speed in space depends on where the measurement is taken and what the spacecraft is being compared with. A vehicle can leave Earth faster than anything before it, then spend the rest of its journey moving more slowly than another probe relative to the Sun. A different spacecraft can hold the absolute speed record for only a few hours near the closest point in its orbit. These records describe different kinds of motion. The fastest departure directly from Earth belongs to New Horizons. It launched from Cape Canaveral on January 19, 2006. An Atlas V rocket and an additional solid-fuel upper stage accelerated the spacecraft away from Earth at roughly 58,000 kilometers per hour. That was about 16 kilometers per second relative to Earth. New Horizons passed the Moon's orbit in approximately 9 hours. The Apollo astronauts had needed about 3 days to cover a similar distance during their journeys to the Moon. The spacecraft was traveling quickly enough to reach Jupiter in just over 13 months. Its launch speed did not come from New Horizons itself. The probe weighed about 478 kilograms and carried only a limited supply of hydrazine fuel for small course corrections and orientation changes. Almost all of its departure energy came from the rocket stages beneath it. After those stages were discarded, New Horizons became a coasting spacecraft. Jupiter provided the next major change. New Horizons reached the giant planet on February 28, 2007. It passed approximately 2.3 million kilometers above Jupiter's cloud tops. The path was planned, so the spacecraft approached the planet while Jupiter was moving forward in its orbit around the Sun. Jupiter's gravity pulled New Horizons inward, curved its trajectory, and released it on a faster outward path. The encounter added approximately 14,000 kilometers per hour to its speed. It also shortened the journey to Pluto by about 3 years. Without the Jupiter encounter, New Horizons would have needed a much slower route through the outer solar system. The gravity assist placed Pluto within reach during July of 2015, around 9.5 years after launch. New Horizons therefore holds a major departure record. Voyager 1 holds a different one. Its launch from Earth in September of 1977 was slower than the departure of New Horizons. Voyager then encountered Jupiter in March of 1979 and Saturn in November of 1980. Those planetary flybys altered its direction and changed its velocity relative to the Sun. The Saturn encounter placed Voyager 1 on a permanent escape trajectory, moving above the broad plane of the planetary system. Today, Voyager 1 travels outward at approximately 17 kilometers per second relative to the Sun. That is around 61,000 kilometers per hour. During 1 year, it increases its distance by roughly 536 million kilometers. Astronomers can express that rate as approximately 3.6 astronomical units per year. 1 astronomical unit is the average Earth-to-Sun distance, close to 150 million kilometers. Voyager 1, therefore, moves outward by more than 3.5 Earth-to-Sun distances every year. New Horizons does not currently increase its distance from the Sun quite as quickly. Its exceptionally fast launch was measured relative to Earth. The later paths of both spacecraft were shaped by planetary motion and solar gravity. Reference frames explain the apparent contradiction. A reference frame is the viewpoint used to measure motion. A person sitting inside a moving train can remain motionless relative to the seat while traveling rapidly relative to the ground. Spacecraft speeds work the same way. A probe can have one velocity relative to Earth, another relative to the Sun, and a different value relative to Jupiter during a flyby. The direction of motion matters as well. Earth circles the Sun at nearly 30 kilometers per second. A spacecraft launched in the same general direction as Earth's orbital motion can begin with part of that speed already helping its solar trajectory. A launch aimed in another direction produces a different result. even when the rocket supplies the same amount of energy. Voyager 2 provides another useful benchmark. It launched on August 20th, 1977, 16 days before Voyager 1. Its longer planetary route carried it past Jupiter, Saturn, Uranus, and Neptune. Voyager 2 remains the only spacecraft to have visited both Uranus and Neptune. Its final Neptune encounter occurred in August of 1989 and placed it on an escape path below the planetary plane. Voyager 2 now moves relative to the Sun at approximately 15.4 kilometers per second. That is slightly slower than Voyager 1. NASA estimates that Voyager 2 would need about 19,390 years to travel 1 light-year at that continuing speed. A departure in 2026 at the same rate would not reach the milestone until around the year 21,416. Voyager 1 would arrive sooner because its escape speed is about 1.6 kilometers per second higher. The difference seems small beside the speed of light. Across trillions of kilometers, it changes the crossing time by nearly 2,000 years. This is why a single list of the fastest spacecraft can be misleading. New Horizons achieved the fastest launch away from Earth. Voyager 1 carries the highest lasting escape speed among the outward-bound probes. The absolute human-made speed record belongs to a spacecraft following a completely different kind of route. Parker Solar Probe reaches almost 11 times Voyager 1's speed during the closest part of its orbit. Using that peak velocity as a permanent interstellar cruising speed would produce a much earlier crossing date. The calculation sounds promising until Parker's path around the Sun is examined more closely. Parker Solar Probe holds the absolute speed record for any human-made object. On December 24, 2024, it swept through the closest point of its orbit around the Sun. That closest point is called perihelion. During the encounter, Parker passed approximately 6.2 million kilometers above the solar surface. Its speed reached about 430,000 miles per hour. That is roughly 692,000 kilometers per hour, or about 192 kilometers every second. At that rate, the probe could cross the distance between New York and Los Angeles in less than 30 seconds. It could travel around Earth's equator more than 17 times during a single hour. Parker was moving almost 11 times faster than Voyager 1's continuing outward speed. Using that record as an interstellar cruising velocity creates a tempting calculation. 1 light-year measures approximately 9.46 trillion kilometers. A spacecraft maintaining 192 kilometers per second would cover that distance in about 1,560 years. A departure in 2026 would therefore cross 1 light-year near the year 3586. That is far sooner than the year 19,661, produced by Voyager 1's speed. The improvement removes more than 16,000 years from the journey. It still leaves the crossing more than 15 centuries in the future. A spacecraft launched while the Roman Empire still controlled parts of Europe would only now be approaching the end of a journey lasting that long. Even this shorter calendar depends on preserving Parker's peak speed after it leaves the inner solar system. Parker cannot do that. Its record velocity comes from the particular shape of its orbit. The spacecraft launched from Cape Canaveral on August 12, 2018. Its mission was designed to study the solar corona, the extremely hot outer atmosphere surrounding the visible surface. Reaching that region required Parker to move much closer to the Sun than any previous spacecraft. A direct inward launch would not have been enough. Earth already travels around the Sun at nearly 30 kilometers per second. Parker inherited that sideways orbital motion when it left Earth. The spacecraft needed to lose much of that motion before it could fall into a tighter solar orbit. Mission planners used repeated flybys of Venus to accomplish this. During each encounter, Venus's gravity changed Parker's orbit and removed some of its angular momentum. Angular momentum describes the motion that keeps an object circling, rather than falling directly inward. Reducing it allowed Parker's closest approach to move progressively nearer to the solar surface. The spacecraft completed 7 planned Venus gravity assists between 2018 and 2024. Its orbit became extremely stretched. The farthest portion remained well away from the solar surface, while perihelion moved deeper into the Sun's gravitational field. As Parker falls inward, gravity accelerates it. The spacecraft begins with gravitational potential energy because of its height above the Sun. That stored energy is converted into kinetic energy as the distance decreases. Kinetic energy is the energy of motion. Near perihelion, much of the available gravitational energy has become speed. Parker reaches its maximum velocity during this brief inner portion of the orbit. The process resembles a ball rolling down a very deep hill. The ball accelerates as it descends because gravitational potential energy becomes motion. If it continues up the other side without an engine supplying extra energy, it slows during the climb. Parker follows the same energy exchange on a much larger scale. After perihelion, the spacecraft moves away from the solar surface. Its kinetic energy begins turning back into gravitational potential energy. The probe slows as it climbs outward. By the time it reaches the distant portion of its orbit, its speed is far below the record measured near the Sun. The velocity has not disappeared through air resistance or friction. It has been exchanged through gravity during the spacecraft's movement through the solar field. Parker remains gravitationally bound to the Sun. A bound orbit returns repeatedly rather than escaping forever. The spacecraft completes another loop and falls inward again, regaining speed as it approaches its next perihelion. Its record belongs to a recurring orbital passage, lasting only a small portion of each revolution. A genuine interstellar departure would require an unbound trajectory. The spacecraft would need enough energy to climb away from the Sun while retaining a large outward velocity after solar gravity had taken back part of the speed gained during the inward fall. Simply pointing Parker away at perihelion would not preserve 192 kilometers per second. Changing its direction that sharply would require an enormous propulsion event. The spacecraft would also need additional energy to escape the solar gravitational field. Parker carries only modest amounts of propellant for orientation and small trajectory corrections. Its heat shield, instruments, solar arrays, and flight plan were designed for repeated close solar encounters. The probe was never equipped with an engine capable of converting its perihelion motion into a permanent interstellar cruise. Its speed record remains valuable because it shows how quickly a spacecraft can move when a massive star supplies the acceleration. It also demonstrates why maximum speed alone does not determine the travel time to 1 light-year. The location of that speed matters. The direction matters as well. A spacecraft racing sideways through perihelion follows a very different future from one moving outward on an escape path. The hypothetical arrival near the year 3586 represents an upper comparison based on a velocity Parker briefly reaches. Producing the same speed on a lasting outward trajectory would require far more energy than the spacecraft carries. Supplying that energy with an onboard engine leads back to a familiar difficulty. The vehicle must accelerate its instruments and structure, along with every kilogram of fuel carried for the journey. The fuel required later must also be accelerated earlier, causing the spacecraft's starting mass to grow much faster than the desired speed. A lasting interstellar speed has to come from somewhere. Parker Solar Probe receives much of its temporary velocity from the Sun's gravity as it falls inward. A spacecraft traveling permanently outward needs enough energy to climb away while keeping a large amount of speed after the climb is complete. For a self-contained rocket, That energy begins with propellant carried aboard the vehicle. A rocket moves by throwing matter backward. Hot gas rushes from the engine nozzle in one direction, and the spacecraft gains momentum in the other. The faster the exhaust leaves, and the more mass the engine expels, the greater the change in the rocket's motion. This principle works in the atmosphere, in Earth orbit, and in the vacuum between planets. The surrounding environment provides no surface for the rocket to push against. The engine pushes on its own exhaust. Every rocket, therefore, begins with several different kinds of mass. The payload is the useful part being transported. For an interstellar probe, that could include cameras, scientific instruments, computers, antennas, shielding, and a power source. The dry mass includes the structure, empty tanks, engines, pipes, insulation, and guidance equipment that remain after the propellant has been used. Propellant is the material consumed by the engines. At launch, the vehicle must accelerate all of them together. A kilogram of propellant intended for use near the end of a burn must first be carried and accelerated through everything that happens earlier. The tanks holding that propellant add more mass. Larger tanks require stronger supports. Those supports also need to be accelerated. This creates the central difficulty described by the rocket equation. The equation links the spacecraft's change in velocity to its exhaust velocity and mass ratio. Velocity change means the total amount by which the rocket can alter its speed over the course of a maneuver. Mass ratio compares the fully fueled mass with the mass remaining after the propellant has been consumed. A rocket with a high mass ratio begins mostly as fuel. As the engines operate, the vehicle becomes lighter because much of that mass leaves through the nozzles. The relationship grows rapidly. Adding twice as much desired velocity does not require merely twice as much propellant when the engine technology remains unchanged. Each increase forces the rocket to carry fuel for moving the fuel already added. The required starting mass can become enormous long before an interstellar speed is reached. Chemical rockets show both the strength and the limitation of this system. Their engines burn substances that react quickly and release large amounts of heat. Liquid hydrogen and liquid oxygen power some upper stages. Kerosene and liquid oxygen have powered vehicles, including the first stage of the Saturn V. Methane is now used in newer rocket designs because it can burn efficiently and may be easier to store or produce during future planetary missions. These reactions create extremely hot, expanding gas. A shaped nozzle directs that gas backward at several kilometers per second. Chemical engines can produce tremendous thrust. Thrust is the force that accelerates the vehicle. The Saturn V generated more than 34 million newtons of thrust at liftoff. That force was sufficient to raise a rocket weighing nearly 3,000 tons from the launch pad and send the Apollo spacecraft toward the moon. High thrust is essential near Earth because the vehicle must climb against gravity while passing through the atmosphere. Efficiency describes a different quality. For a rocket engine, efficiency is closely connected to exhaust velocity. An engine that throws each kilogram of propellant backward more quickly can produce a larger total velocity change from the same amount of fuel. Chemical reactions place a ceiling on how fast their exhaust can realistically move. The available energy comes from rearranging electrons within molecules. That energy is powerful enough to launch spacecraft from Earth, yet it remains modest compared with nuclear reactions or matter converted directly into energy. A chemical rocket can accelerate a probe to tens of kilometers per second under favorable conditions. 1% of light speed is almost 3,000 kilometers per second. 10% is nearly 30,000 kilometers per second. The gap cannot be closed by attaching a slightly larger tank to a conventional rocket. The vehicle would become dominated by propellant before reaching anything close to those speeds. Staging helps manage this problem. A launch vehicle is divided into sections that operate one after another. When a stage has emptied its tanks, the rocket discards the engines, structure, and plumbing connected to it. The remaining stages no longer need to accelerate that dead mass. The Saturn V used 3 main stages during its climb from Earth. Modern launch vehicles follow the same broad principle, although their engines, fuels, and recovery systems differ. Staging improves performance because empty hardware is removed at the earliest useful moment. It does not erase the rocket equation. Every stage still carries and accelerates the stages above it. An interstellar chemical rocket assembled in space could avoid lifting all of its fuel from Earth's surface. It could also use several stages and begin far from the atmosphere. Those advantages would improve the final escape speed. The improvement would remain modest beside the 1 light-year requirement. A journey lasting 17,000 years might be shortened by centuries, or perhaps several thousand years, under an extreme design. A human lifetime crossing would demand speeds hundreds of times greater than those reached by present outward-bound probes. The obstacle is woven into the propulsion method. The spacecraft carries the material it will later throw away, and that material must share every earlier acceleration. Engineers have already learned to supplement onboard fuel with energy and momentum found elsewhere in the solar system. A moving planet contains an immense supply of orbital momentum. By approaching from the correct direction and passing through its gravity, a spacecraft can leave faster without burning the amount of propellant that the same change would otherwise require. Jupiter carries an enormous amount of motion as it travels around the Sun. The planet orbits at roughly 13 kilometers per second. A spacecraft can use a small part of that motion without carrying the equivalent energy as fuel. The maneuver is called a gravity assist. Its success depends on timing, direction, and the planet's own movement through space. Imagine a spacecraft approaching Jupiter from behind, while the planet moves along its orbit. Jupiter's gravity begins pulling on the craft long before the closest approach. The spacecraft falls inward, gains speed, and follows a curved path around the planet. During the encounter, Jupiter keeps moving forward. The spacecraft leaves from a different direction and with a different velocity relative to the Sun. From Jupiter's local point of view, the craft generally departs with about the same speed it had on arrival. The larger gain appears when the motion is measured relative to the Sun, because the spacecraft has exchanged a tiny amount of momentum with a moving planet. Momentum combines mass with velocity. Jupiter contains more than 300 times Earth's mass, so the exchange produces no measurable change in the planet's orbit. The spacecraft is many orders of magnitude lighter. A minute loss from Jupiter can become a large gain for the probe. Voyager 1 used this technique during one of the most carefully timed mission designs in spaceflight history. During the late 1970s, Jupiter, Saturn, Uranus, and Neptune occupied a rare arrangement that allowed a spacecraft to pass from one outer planet to the next. A similar alignment occurs only about once every 176 years. NASA used the opportunity to create the Voyager Grand Tour. Voyager 1 reached Jupiter in March of 1979. The spacecraft approached the planet on a path chosen to satisfy 2 goals at once. Its instruments needed useful views of Jupiter and the major moons. Its exit path also had to point towards Saturn. Jupiter's gravity bent Voyager's trajectory and raised its speed relative to the Sun. The encounter sent the probe across the gap towards Saturn in less than 2 years. Voyager 1 arrived at Saturn in November of 1980. The mission then faced an important choice involving Titan. Titan is Saturn's largest moon and the only moon in the solar system with a thick atmosphere. Scientists wanted Voyager to pass close enough to measure that atmosphere and examine the moon in detail. The selected path carried the spacecraft only about 6,500 kilometers above Titan's surface. Titan's gravity and the geometry of the Saturn encounter changed Voyager's direction sharply. The spacecraft left the planetary plane on a path tilted northward. That decision ended any possibility of continuing toward Uranus or Neptune. Voyager 2 followed a different route and eventually visited both planets. Voyager 1 gained something else. Its Saturn encounter placed it on the permanent escape trajectory it still follows today. The spacecraft continues moving away from the Sun at roughly 17 kilometers per second. That lasting escape speed was shaped by planetary motion rather than by a long engine burn after Saturn. New Horizons provides a cleaner example because the speed change was measured during a single well-known encounter. The spacecraft launched in January of 2006 and reached Jupiter on February 28, 2007. It passed behind the planet in the correct direction for an outward boost. Jupiter's gravity increased New Horizons' speed by approximately 14,000 kilometers per hour. That gain shortened the journey to Pluto by about 3 years. The spacecraft reached Pluto in July of 2015. Without Jupiter, the mission would have needed a slower route or a much more demanding launch. Gravity assists can also reduce speed. A spacecraft approaching a planet from the opposite direction can transfer some of its momentum to the planet. Mission designers use this form when a probe must fall deeper into the solar system. Parker Solar Probe used repeated encounters with Venus to reduce the sideways motion it inherited from Earth. Each flyby helped lower Parker's perihelion until the spacecraft could pass extremely close to the Sun. The same mechanism can therefore accelerate a craft outward or reshape its orbit inward. Trajectory determines the result. Planetary assists remain limited by the worlds available along the route. A spacecraft must reach the correct planet at the correct time and pass through a narrow region of space. Arriving too early or too late changes the geometry. Passing on the wrong side can reduce speed when the mission needs an increase. The planet's gravity also places practical limits on how close the spacecraft can safely travel. Atmospheres, radiation belts, moons, and rings can restrict the path. Mission planners sometimes combine gravity with a brief engine burn. The deeper physical advantage is called the Oberth effect. An engine produces a certain local change in speed when it burns a fixed amount of propellant. That same change can produce a larger increase in orbital energy when the spacecraft is already moving rapidly near a massive body. Near perihelion, a spacecraft may be traveling several times faster than it does in the outer part of its orbit. A burn performed there adds its velocity change at the moment, when the craft already carries the most kinetic energy. The result can raise the distant part of the orbit far more than an identical burn made farther away. This does not create free energy. The engine still consumes propellant, and the spacecraft still receives the same immediate push. The timing allows that push to change the shape and energy of the solar orbit more effectively. Proposed interstellar precursor missions sometimes combine a close solar passage, heat-resistant shielding, and propulsion near perihelion. The spacecraft falls inward, gains speed from gravity, performs its burn near the closest approach, and leaves on a much faster outward path. Such designs could exceed Voyager's escape speed by a wide margin. They would still begin inside the same planetary system and depend on the gravitational machinery already moving around them. Once the final planet and the Sun's deepest useful passage are behind the craft, there are no larger nearby worlds waiting to provide another easy boost. The engines fall silent, the planets shrink into distant points, and the spacecraft enters a region where the familiar map of the solar system has barely begun. Beyond Neptune, the familiar planetary map begins to thin out. Neptune travels around the Sun at an average distance of about 30 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, close to 150 million kilometers. Neptune is therefore about 4.5 billion kilometers from the center of the solar system. It takes sunlight a little more than 4 hours to reach the planet. A spacecraft passing Neptune has crossed the region occupied by the 8 major planets, but it has not reached a single final edge. The first large structure beyond Neptune is the Kuiper Belt. This broad zone begins near Neptune's orbit and extends outward to roughly 50 astronomical units, with scattered objects reaching much farther. It contains countless bodies left over from the formation of the solar system. Most are mixtures of rock and frozen materials such as water ice, methane, and ammonia. Pluto belongs to this region. So do the dwarf planets Haumea and Makemake. Eris follows a more distant and strongly tilted orbit that carries it far beyond the main belt. These objects occupy only a tiny fraction of the available space. A spacecraft moving through the Kuiper Belt would not weave between crowded worlds. Most of the journey would remain almost completely empty. The Sun still shapes the environment there through gravity, light, and a constant stream of particles called the solar wind. The solar wind begins in the corona, the extremely hot outer atmosphere of the Sun itself. Temperatures in the corona reach more than 1 million degrees Celsius. At those temperatures, atoms are stripped apart into charged particles. This electrically charged gas is called plasma. The plasma flows outward in every direction at hundreds of kilometers per second. Near Earth, a typical solar wind speed is around 400 kilometers per second, although faster streams can exceed 700. The wind carries part of the Sun's magnetic field with it. Because the Sun rotates, those magnetic field lines become curved into a spiral extending throughout the planetary system. Together, the solar wind and its magnetic field create the heliosphere. The heliosphere is an enormous bubble embedded within the thinner material between the stars. Earth, Mars, Jupiter, and the other planets orbit inside this bubble. It provides partial protection from galactic cosmic rays, which are high-energy particles arriving from distant events such as exploding stars. The solar wind does not maintain the same speed forever. As it expands, it becomes thinner and encounters pressure from the interstellar medium. The interstellar medium is the sparse gas, dust, magnetic fields, and radiation occupying the space between star systems. Far beyond the planets, the solar wind begins to slow. Voyager 1 detected this change on December 16, 2004, at approximately 94 astronomical units from the Sun. The boundary it crossed is called the termination shock. At the termination shock, the solar wind drops from a speed faster than the waves traveling through the plasma to a slower, compressed flow. The region beyond is called the heliosheath. There, heated solar plasma continues moving outward, while being pressed and redirected by the material surrounding the heliosphere. Voyager 1 spent almost 8 years crossing the heliosheath. On August 25, 2012, its instruments recorded a lasting change at approximately 121 astronomical units from the Sun. The number of particles originating from the solar wind fell sharply. Galactic cosmic rays became more intense. Measurements showed that Voyager had crossed the heliopause. The heliopause is the outer surface, where the pressure of the solar wind balances the pressure of the surrounding interstellar medium. Beyond it, the local plasma and magnetic environment is shaped mainly by the galaxy rather than by the solar wind. Voyager 1 had entered interstellar space. The crossing occurred nearly 35 years after launch, and about 18 billion kilometers from the Sun. Voyager 2 reached the same kind of boundary on November 5, 2018. Its crossing occurred at approximately 119 astronomical units. The different locations showed that the heliopause is not a perfectly fixed sphere. Solar activity can make the boundary expand or contract. Its shape also responds to magnetic fields and changing conditions in the nearby interstellar medium. Both Voyager spacecraft now operate outside the heliosphere. Their instruments directly sample particles and magnetic fields in interstellar space. That achievement is often described as leaving the solar system. The phrase is accurate under one useful definition. The Voyagers have left the region dominated by the solar wind. A different definition produces a much larger solar system. The gravity of the Sun extends far beyond the heliopause. Gravity weakens with distance, but it does not suddenly stop at 120 astronomical units. An object thousands of astronomical units away can still move in a long orbit around the Sun. Its orbital period may last millions of years, yet the object remains gravitationally connected to the solar system. This creates several legitimate edges. Neptune marks the outer boundary of the major planets. The heliopause marks the end of the solar wind bubble. A gravitational edge lies much farther away, where passing stars and the Milky Way's own gravity become more influential than the pull of the Sun. The exact location of that distant boundary changes with direction and with the motion of nearby stars. There is no single shell where every form of solar influence ends at once. Voyager 1 has crossed into interstellar space while remaining deep inside the Sun's wider gravitational territory. At its present distance, it has traveled a little more than 160 astronomical units from the Sun. The tidal milestone lies near 63,241 astronomical units. That is almost 400 times farther than Voyager's current position. Across part of that distance may lie a vast population of distant icy bodies. Their estimated orbits extend so far from the planets that one complete light year may still end before the solar system's outermost comet reservoir does. The distant comet reservoir surrounding the solar system may overlap the 1 light-year boundary itself. Astronomers call this region the Oort Cloud. It is thought to form a vast, roughly spherical population of icy bodies surrounding the Sun in every direction. That shape makes it very different from the planetary system closer to home. Mercury, Venus, Earth, and the other planets follow orbits arranged within a broad, flattened plane. The Kuiper belt beyond Neptune follows the same general structure, although its objects occupy a thicker and more disturbed region. The Oort cloud may extend above and below that plane until the solar system resembles a tiny planetary disk surrounded by an enormous sphere of scattered ice. No spacecraft has visited it. No telescope has photographed the entire cloud. Its objects are too small, too dark, and too far away to be counted directly. Astronomers infer its existence mainly from long-period comets. These are comets that may need thousands, hundreds of thousands, or even millions of years to complete a single orbit. Some arrive from steep angles that do not match the flatter arrangement of the planets. Their paths suggest they began in a distant spherical reservoir rather than in the Kuiper belt. One famous example is Comet Hale-Bopp. It became bright enough to see without a telescope during 1997. Its orbital period is now estimated at roughly 2,500 years after its passage through the inner solar system. Other long-period comets follow paths so extended that they may not return for tens of thousands of years. These objects spend almost all of their existence in extreme cold and darkness. A disturbance can change that. A passing star may pull gently on a distant comet. The Milky Way itself also produces a weak gravitational effect called the galactic tide. This tide comes from the combined gravity of stars, gas, and dark matter across the galaxy. It acts very slowly, but Oort cloud objects are so weakly held that even a small disturbance can alter their orbits. Some are pushed farther outward and lost. Others begin a long fall toward the planets. As one approaches the inner solar system, sunlight warms the frozen surface. Ice changes directly into gas through a process called sublimation. Escaping gas carries dust with it, producing the coma and tail that make a comet visible. The bright object crossing Earth's sky may therefore have spent millions of years near the outer limits of the solar system before beginning its inward journey. The estimated scale of that reservoir is enormous. NASA commonly describes the Oort Cloud as beginning around 5,000 astronomical units from the Sun. Its outer extent may reach approximately 100,000 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, close to 150 million kilometers. The inner edge of the Oort Cloud would therefore lie around 750 billion kilometers away. The outer estimate reaches about 15 trillion kilometers. 1 light-year equals roughly 63,241 astronomical units. That places the tidal milestone well beyond the estimated inner Oort Cloud. It also places the milestone inside the highest commonly used estimates for the cloud's outer extent. An outer boundary near 100,000 astronomical units would reach approximately 1.6 light-years from our star. A spacecraft could therefore travel 1 complete light-year and remain inside a region containing objects gravitationally associated with the solar system. The word containing needs careful interpretation. The Oort Cloud would look almost completely empty. Its total population may include trillions of icy bodies larger than about 1 kilometer, along with many smaller objects. Those bodies are spread through a volume measured in light-years. The average separation could be billions of kilometers. A spacecraft would not enter a bright wall of comets. Its cameras would probably see only stars, unless it happened to pass unusually close to one of the dark objects. The Sun would still appear as the brightest star behind it, though its light and warmth would have become extremely weak. At 5,000 astronomical units, sunlight is 25 million times dimmer than it is near Earth. At 63,000 astronomical units, the reduction is almost 4 billion times. An Oort Cloud object at that distance may have a temperature only a few tens of degrees above absolute zero. Water, carbon dioxide, methane, and carbon monoxide would remain frozen for immense periods. Voyager 1 is traveling toward this distant region at about 17 kilometers per second. At that speed, it may need roughly 300 years to reach the estimated inner Oort Cloud. Passing through the entire structure could require about 30,000 years. The spacecraft may therefore cross 1 light-year before reaching the cloud's most distant estimated edge. Its path will also matter. The Oort Cloud is probably uneven. Passing stars, galactic tides, and the early migration of the giant planets may have stretched or disturbed parts of it. The outer boundary may vary with direction, and many distant objects may follow loose orbits that are easily changed. The term cloud describes a statistical population rather than a sharply defined object. There may be no precise moment when Voyager enters it. There may be no precise moment when it leaves. This changes the meaning of the title milestone. 1 light-year sounds like the beginning of the space between star systems. Under the broadest gravitational definition, the spacecraft may still be traveling through the outskirts of its original solar system. Its engines could be silent. Its power might be gone. Momentum alone would continue carrying the metal structure through a region where a single orbit can last millions of years. Crossing the distance as an intact object is one challenge. Crossing it while still operating requires a machine able to survive far beyond the lifetime of any spacecraft ever built. An object drifting through the Oort Cloud needs no electricity to keep moving. Once it has gained enough speed, momentum can carry it onward for thousands of years. A scientific spacecraft has a much harder job. It must generate power, control its orientation, operate instruments, store information, and transmit signals across an ever-growing distance. Voyager 1 provides the longest-running practical test of that problem. The spacecraft carries 3 radioisotope thermoelectric generators. These generators use plutonium-238, a radioactive material that releases heat as its atoms slowly decay. Thermocouples convert part of that heat directly into electricity. A thermocouple is a device made from different conducting materials. When one side is hot and the other is cooler, an electric voltage appears between them. Voyager's generators contain no turbines or moving pistons. That simplicity has helped them continue operating since September of 1977. At launch, the 3 generators supplied approximately 470 watts of electrical power. That was less than the power used by many household appliances. It was enough to operate Voyager's computers, heaters, scientific instruments, radio transmitter, and attitude control systems. The available electricity has declined steadily ever since. Voyager loses roughly 4 watts of usable power each year. Part of that decline comes from the plutonium itself. Plutonium-238 has a half-life of approximately 88 years. A half-life is the time required for half of a radioactive material's atoms to decay. After one half-life, the fuel continues producing heat, but at about half its original rate. Voyager has not yet traveled for 88 years. Its electrical output has still fallen faster than the radioactive decay alone would suggest. The thermoelectric materials also age. Repeated heating and cooling change their performance. Connections develop resistance. Insulating materials weaken after decades of radiation exposure and extreme temperature changes. The heat remains, but a smaller fraction can be converted into electricity. Engineers respond by reducing the spacecraft's power demands. Heaters have been turned off where equipment can tolerate the cold. Scientific instruments have been shut down one at a time. Additional shutdowns during 2025 and 2026 preserved electricity for the systems still considered most valuable. Every saving extends the mission, although each one also removes part of Voyager's ability to observe its surroundings. Power is only one limit. The spacecraft's electronics were designed during the 1970s. Its computers use components built long before modern radiation-hardened processors existed. Charged particles can strike memory cells and alter stored information. Engineers sometimes correct these errors by sending updated commands from Earth. A probe crossing 1 light-year over 17,000 years could not depend on a support team repairing its software from home. Mechanical systems age in different ways. Voyager uses small thrusters to keep its large antenna pointed toward Earth. Those thrusters fire by releasing hydrazine propellant. Valves must open correctly after years of inactivity. Fuel lines must remain clear. Tiny amounts of residue can accumulate inside the system. Lubricants may evaporate or become less effective in vacuum. Insulation can become brittle under radiation. Repeated temperature changes place stress on joints and electrical connections. The spacecraft's metal frame may remain recognizable long after these systems fail. Aluminium and titanium can persist for immense periods in the near vacuum of interstellar space. There is no rain to cause weathering, and almost no oxygen to produce ordinary rust. Sparse atoms and dust grains slowly strike the forward surfaces, while cosmic radiation changes materials molecule by molecule. Physical survival can therefore last much longer than useful operation. A silent Voyager could continue coasting after its transmitter fails. Its dish might still point roughly toward Earth. The scientific instruments could remain attached to the frame. Without power and functioning control systems, the vehicle would have become a relic rather than an active probe. A spacecraft designed to operate for millennia would need a different architecture. Several independent power systems could be activated at different stages of the journey. Most electronics might remain dormant for centuries. protected inside shielded compartments until scheduled wake periods. Computers would need to detect faults, compare duplicate systems, and decide which components could still be trusted. Replaceable modules could allow robotic mechanisms to remove damaged equipment and install stored spares. A still more advanced craft might manufacture simple replacement parts from material carried aboard. Long-term data storage would present its own difficulty. Magnetic memory can lose information. Electronic charge gradually leaks from some storage devices. Optical materials can be damaged by radiation. Mission records may need to be copied repeatedly into fresh storage, with several versions checked against one another for errors. The spacecraft would also need an internal standard for time. Clocks drift. Radiation changes electronic components. A mission lasting thousands of years may require several timing methods, perhaps including atomic clocks and observations of pulsars. All of this increases mass and power consumption. Redundancy adds duplicate hardware. Shielding adds more material. Repair systems require tools, spare parts, and computers capable of making decisions no engineer can supervise in real time. A metal object can cross 1 light-year through momentum alone. An operating spacecraft must preserve a chain of functioning systems across a period longer than any human institution has existed. Even a machine that survives those demands would still need to determine where it is. The Sun will have moved through the Milky Way. Nearby stars will have shifted, and the invisible 1 light-year boundary must be located within a sky that no longer matches the map used at launch. By the time the spacecraft has traveled deep into the Oort Cloud, the Sun has become one bright star among many. Its light still identifies the direction of home, but its apparent position alone cannot tell the craft exactly where it is. Navigation requires a continuing estimate of position, speed, and direction. Spacecraft near Earth receive much of that information through radio tracking. NASA's Deep Space Network uses large antennas in California, Spain, and Australia. Their locations are spread around Earth so at least one complex can communicate with a distant mission as the planet rotates. A tracking station can send a carefully timed radio signal toward a spacecraft. The spacecraft receives the signal and transmits a response. By measuring how long the complete exchange takes, controllers can estimate the distance. This method is called radio ranging. The measurement must account for delays inside the electronics and the motion of Earth during the signal's journey. The radio frequency also changes slightly when the spacecraft moves toward or away from the receiving antenna. This is the Doppler effect. The same effect changes the pitch of a passing siren, although spacecraft navigation measures radio waves rather than sound. A rising or falling frequency reveals the spacecraft's motion along the line between the vehicle and Earth. Repeated measurements allow navigators to estimate its velocity with great precision. Position and velocity are then fed into mathematical models containing the gravity of the Sun, planets, moons, and other relevant bodies. Those models predict where the spacecraft will travel next. Small engine burns, called trajectory corrections, keep the mission close to its planned route. Voyager performed these corrections during its planetary encounters. New Horizons used them while approaching Pluto, where a small error could have moved its cameras away from the narrow region containing the dwarf planet and its moons. A light-year journey allows small errors far more time to grow. Direction is measured through angles. A single degree can be divided into 60 arc minutes. Each arc minute can be divided into 60 arc seconds. 1 arc second is therefore 1/3600th of a degree. That angle appears extremely small in the sky. Across 1 light year, a straight line pointing error of 1 arc second would produce a sideways displacement of roughly 46 million kilometers. That is more than 100 times the average distance between Earth and the Moon. A slightly larger error of 1,000th of a degree would widen to about 165 million kilometers. That is greater than the average distance between Earth and the Sun. Real navigation does not allow an initial error to grow without correction. The comparison shows why the craft must keep checking its path. Star trackers provide one method. A star tracker is a camera designed to recognize patterns of stars. Its onboard catalog contains the measured positions and brightnesses of selected stars. The computer compares the observed pattern with the catalog and calculates the spacecraft's orientation. This allows the vehicle to point an antenna toward Earth, aim an instrument at a target, or align an engine before a correction burn. Gyroscopes help measure changes between those observations. A gyroscope senses rotation. Modern spacecraft often use spinning wheels or optical devices that detect extremely small turns. These systems can guide a spacecraft when a star tracker is temporarily unavailable, although their measurements slowly drift and must be corrected using external references. A mission lasting 17,000 years cannot rely on the same star catalog forever. Stars move through the Milky Way. Their gradual change in apparent position is called proper motion. The movement is usually tiny during a human lifetime, but it becomes obvious across centuries or millennia. Barnard's star provides a strong nearby example. It shifts across Earth's sky by more than 10 arcseconds each year. That is the largest known proper motion of any star. During a century, it moves by nearly 1/3 of a degree, enough for precise navigation software to notice easily. The constellations also change. Their familiar patterns come from stars located at very different distances and moving along different paths. A spacecraft launched in 2026 cannot compare the sky thousands of years later with a frozen map from launch. Its catalog must predict future stellar positions or rebuild the map from fresh observations. Pulsars could provide a more stable galactic reference. A pulsar is the dense rotating core left behind after a massive star explodes. Many are only about 20 kilometers wide, while containing more mass than the Sun itself. Their magnetic fields produce beams of radiation that sweep through space as the object rotates. When a beam passes Earth or a spacecraft, it appears as a pulse. Some pulsars rotate hundreds of times each second. The most stable examples are called millisecond pulsars. Their pulse timing can remain regular enough to act like natural clocks distributed across the galaxy. A spacecraft could observe several pulsars, compare the arrival times of their pulses with stored predictions, and estimate its position without contacting Earth. The method resembles satellite navigation on Earth, although the beacons are distant neutron stars rather than human-built satellites. Autonomous navigation would still need to account for the motion of the destination reference point. The Sun travels around the Milky Way under the galaxy's gravity. The spacecraft also remains inside that gravitational field. Both trajectories curve gradually as they move around the galactic center. The craft carries the solar system's galactic motion with it at launch, then adds its own escape velocity in a different direction. The separation between them develops through two moving paths, rather than one object leaving a stationary marker. Nearby stars also produce small gravitational effects. A close stellar passage during a journey lasting many millennia could alter the spacecraft's path or disturb distant Oort Cloud bodies. Navigators would update the predicted trajectory whenever new measurements showed a difference from the model. The 1 light-year crossing would finally be determined by comparing the spacecraft's calculated position with the Sun's calculated position at the same moment. Neither position remains fixed. There is no permanent road to follow and no stationary finish line waiting ahead. The spacecraft must keep measuring the changing sky, correcting its internal clock, and rebuilding its estimate of the journey. Earth can help while communication remains practical. Each kilometer added to the distance makes that assistance arrive a little later. At the 1 light-year boundary, a navigation report sent home will spend 1 full year traveling toward Earth, and any instructions sent back will require another year to return. That growing delay already controls the way Voyager 1 is operated. By 2026, a command sent from Earth requires roughly 23 hours to reach the spacecraft. The same amount of time passes before Voyager's reply returns. A simple exchange, therefore, stretches across almost 2 full days. Mission controllers prepare each command carefully before transmission. Voyager's remaining electrical power is limited. Its instruments are aging, and an incorrect instruction cannot be corrected quickly. Engineers may send a command during 1 working day and wait until the following day to learn whether the spacecraft received it. Any response reporting the result arrives almost another day after that. The signal itself moves as quickly as nature allows. Radio waves are a form of electromagnetic radiation, belonging to the same family as visible light. Both travel through empty space at approximately 300,000 kilometers per second. The delay comes entirely from distance. Voyager 1 is so far away that even light needs almost a day to reach it. As the spacecraft continues outward, the delay increases in a steady and predictable way. At 2 light days from Earth, a command needs 2 days to arrive. 10 light days create a 10-day journey in each direction. 1 light month produces a delay of roughly 1 month. The spacecraft could receive a warning after the event that caused it had already been developing for weeks. At 6 light months, Earth and the probe would be separated by half a year of signal travel. An instruction transmitted in January might reach the spacecraft during July. A reply sent immediately would not return until the following January. The crossing at 1 light year extends the same process to a complete year. A command sent from Earth at the moment the spacecraft reaches the boundary arrives 1 year later. If the craft processes the instruction and transmits a response immediately, Earth receives that answer after another year. 1 complete exchange requires 2 years. Any delay aboard the spacecraft makes the conversation longer. A scientific observation may need to be checked before transmission. A computer may need time to compress the data. The antenna may have to turn away from its normal direction and hold a precise angle toward the solar system. Every operation occurs inside a conversation, already separated by years. Distance also weakens the received signal. Radio energy spreads outward as it travels. A narrow beam begins with a limited width, then gradually expands because no real antenna can focus the transmission into a perfectly straight line. The same total energy becomes distributed across a larger area. This follows the inverse square law. Doubling the distance spreads the energy across roughly 4 times the area. Tripling the distance spreads it across about 9 times the area. A receiving antenna therefore captures a smaller fraction of the original transmission as the spacecraft moves farther away. Voyager's radio transmitter produces only about 23 watts. That is comparable to the power used by a small household light. Its large dish directs much of that radio energy toward Earth, rather than allowing it to spread equally in every direction. After traveling for billions of kilometers, the signal arriving at Earth is extraordinarily faint. Large antennas collect the weak radio waves and sensitive electronics separate them from background noise. At 1 light year, a similar transmitter would be far more difficult to detect. The distance would be hundreds of times greater than Voyager's present separation. Signal strength would fall by the square of that increase. An active probe could compensate with a more powerful transmitter, a larger antenna, or a narrower beam. Each solution creates engineering costs. Higher transmitter power demands a larger energy supply. A bigger dish adds mass and must retain its shape with extreme precision. A narrower beam requires more accurate pointing because even a small angular error can send the transmission far past Earth. Laser communication offers another approach. A laser can concentrate light into a beam narrower than most radio transmissions. That allows more of the transmitted energy to reach the intended receiver. The spacecraft would need to hold the beam on a distant moving target with extraordinary accuracy. Earth occupies a tiny angle when viewed from 1 light-year away. The receiving observatory also moves as Earth rotates and circles the Sun. Clouds and atmospheric turbulence can interfere with ground-based laser communication, which may require several observatories or receivers placed in space. Radio and laser systems share the same basic limit. Their information travels at light speed. A more powerful transmitter can improve signal strength. A larger receiver can collect more energy. Neither can shorten the 1-year propagation time. This changes how the spacecraft must respond to danger. A fault in the power system cannot wait 2 years for instructions. A navigation error must be recognized before it grows. If a micrometeoroid damages an instrument, the craft has to isolate the failed equipment and protect the rest of the vehicle on its own. Onboard computers would compare sensor readings, identify abnormal behavior, and choose from repair procedures written centuries or millennia earlier. Some decisions could be prepared before launch. Others would involve combinations of failures no engineer predicted. A long-duration spacecraft may need software capable of testing possible responses through simulation before taking action. It may also require several independent computers that can compare results and prevent one damaged system from controlling the entire mission. Communication with Earth would remain useful. Scientists could receive measurements from regions no spacecraft had explored before. Future engineers could send improved instructions based on knowledge developed after launch. The relationship would resemble correspondence across time rather than direct control. Earth would learn what happened long after the event. The spacecraft would receive advice from a version of Earth 1 year in its past. At the boundary, both sides remain connected, yet neither can react to the other's present condition. A 2-year exchange already changes the nature of a mission. The larger calendar remains far more severe. For a spacecraft moving at Voyager 1's speed, this distant conversation begins only after more than 17,000 years of travel. The signal announcing the crossing would begin its return journey through a very different sky. A Voyager speed spacecraft, launched in 2026, would need roughly 17,600 years to travel 1 light-year. When its transmitter finally sent confirmation toward home, the radio message would require 1 additional year to reach Earth. The arrival date would fall near the year 19,661. That interval is long enough for a measurable change in the orientation of our planet itself. Earth spins around an axis passing through the North and South poles. The axis is tilted by about 23.5 degrees relative to the plane of Earth's orbit. That tilt produces the seasons as the planet moves around the Sun each year. The direction of the axis also changes slowly. Instead of pointing toward the same place in the sky forever, it traces a broad circle over approximately 26,000 years. This motion is called axial precession. A useful comparison is a spinning top. When the top begins to lean, its axis slowly sweeps around rather than remaining fixed in one direction. Earth performs a far slower version of that motion. Our planet is slightly wider around the equator than it is from pole to pole. This equatorial bulge gives the gravity of the Moon and the Sun a shape to pull against. Their gravitational torques gradually turn the direction of Earth's axis. A torque is a twisting force. The effect during a single year is tiny. Across thousands of years, the change becomes large enough to rearrange the position of the celestial poles. At present, Earth's northern axis points close to Polaris. Polaris lies a little less than 1 degree from the north celestial pole. That makes it appear almost stationary while the rest of the northern sky turns around it each night. Navigators have used its position for centuries because it provides a reliable indication of north. The match is temporary. Several thousand years ago, the axis pointed closer to Thuban, a star in the constellation Draco. Ancient Egyptians living during the construction of the largest pyramids saw a northern sky centered nearer to Thuban than Polaris. Thousands of years from now, the axis will continue moving away from Polaris. Vega, the bright star in the constellation Lyra, will eventually lie much closer to the northern celestial pole during a later part of the precession cycle. Vega is currently about 25 light-years from Earth and appears as one of the brightest stars in the summer sky of the northern hemisphere. It will never sit as close to the pole as Polaris does today, but it will become a prominent northern reference roughly 12,000 years from now. A journey lasting 17,600 years spans more than 2/3 of one complete precession cycle. The northern pole at the time of crossing would point toward a region of sky far removed from its position at launch. Polaris would still exist unless an unexpected event changed it, but it would no longer serve as the familiar fixed marker above Earth's north. The constellations would also have changed shape. Stars move through the galaxy at different speeds and in different directions. Their gradual motion across our sky is called proper motion. Over a few decades, most of those shifts are difficult to notice without precise instruments. Across 17 millennia, several familiar patterns would become distorted. The stars of the Big Dipper would no longer form exactly the same outline. Nearby stars with high proper motion would occupy visibly different positions. The sky used by the launch engineers would no longer match the sky seen when the signal returned. Human records would face a different kind of drift. The oldest known writing systems appeared a little more than 5,000 years ago in places including Mesopotamia and ancient Egypt. A Voyager speed crossing would last more than 3 times that entire span. Languages can change beyond easy recognition in much shorter periods. Modern English speakers already need training to read Old English texts written about 1,000 years ago. The language spoken in England during the time of Alfred the Great uses different vocabulary, grammar, and pronunciation from the language used today. Across 17,000 years, preserving the original mission instructions would require repeated translation into languages that do not yet exist. Digital storage would also need active care. Hard drives, magnetic tape, optical discs, and solid-state memory all degrade on timescales far shorter than the journey. A mission archive would have to be copied again and again onto new media. Each transfer would need error checking to prevent small mistakes from accumulating. The meaning of technical terms would need to be preserved alongside the data. A future receiver might capture the spacecraft's signal perfectly and still need historical records to understand the encoding, units, and purpose of the transmission. Institutions would face the same problem. NASA was created in 1958. The Voyager program began less than 20 years later. Maintaining one organization for 17,000 years would exceed the lifetime of every known government, university, scientific academy, and religious institution. Continuity would probably depend on many successor organizations rather than one uninterrupted agency. Calendars could change. Political borders could change. The receiving antennas might stand on continents whose coastlines and ecosystems had shifted. Even if humanity remained technologically advanced, the original mission could arrive as a message from a remote ancestral age. The crossing itself would still be physically precise. The spacecraft would reach the measured distance. Its transmission would carry a timestamp according to the clock aboard. Earth would record the signal 1 year later. Understanding what the event meant would depend on a chain of memory stretching across more than 17 millennia. Reducing that interval to a century, a decade, or only a few years requires a completely different class of propulsion. The first practical step away from brief chemical burns is an engine that applies a very small force for years, allowing speed to accumulate long after launch. A chemical rocket produces most of its useful acceleration during a brief period near the beginning of a mission. Its engines may burn for minutes before the spacecraft spends years coasting. Ion propulsion stretches that process across months or even years. The force is extremely small, yet it continues long enough for the accumulated change in speed to become substantial. Deep Space One became one of the first major demonstrations of this approach. NASA launched the spacecraft from Cape Canaveral on October 24, 1998. Its primary purpose was to test technologies that had not yet been used together on a deep space mission. The most important was an ion engine called the NASA Solar Technology Application Readiness System. The engine used xenon, a heavy noble gas that remains chemically stable and is relatively easy to store. Inside the engine, electrons collided with xenon atoms and removed some of their electrons. This gave the atoms an electric charge. Charged atoms are called ions. Electric fields then accelerated the xenon ions through a set of metal grids and expelled them from the rear of the spacecraft. The outgoing ions formed the engine's exhaust. A separate device released electrons into that exhaust so the spacecraft would not build up an electrical charge. The thrust was gentle. Deep Space One's engine produced roughly 90 millinewtons at full power. That is about the force created by the weight of a small sheet of paper resting in a person's hand. Such a push would barely move a spacecraft during its first second of operation. After a day, the difference becomes measurable. Months of continuous thrust allow the speed to keep increasing. Ion engines use propellant efficiently because their exhaust leaves at tens of kilometers per second. Chemical rocket exhaust generally travels much more slowly. Faster exhaust allows each kilogram of propellant to create a larger total velocity change. Deep Space One operated its ion engine for more than 16,000 hours. The spacecraft flew past the asteroid Braille in July of 1999. It later approached Comet Borrelly in September of 2001 and returned some of the clearest images then available of a comet's dark, elongated nucleus. The mission showed that a low-thrust engine could guide a spacecraft through several years of changing trajectories. Dawn expanded that achievement into a much more demanding journey. The spacecraft launched on September 27, 2007. It carried 3 ion engines and about 425 kilograms of xenon propellant. Only one engine operated at a time. At maximum power, each produced about 90 millinewtons of thrust, similar to the engine flown on Deep Space One. Dawn's acceleration was so slight that gaining the speed of a highway car required several days. The engine could continue operating for thousands of hours without exhausting its propellant. That endurance allowed Dawn to accomplish something no previous spacecraft had done. It entered orbit around the asteroid Vesta in July of 2011. After studying Vesta for more than a year, the spacecraft used its ion engines to leave orbit and continue toward Ceres. Dawn reached Ceres in March of 2015 and entered orbit around the dwarf planet. A conventional chemical spacecraft would have needed far more propellant to break into orbit around Vesta, escape again, and then break a second time at Ceres. Ion propulsion supplied approximately 11.5 kilometers per second of accumulated velocity change during the mission. Its engines operated for roughly 6 years in total. That velocity change is comparable to much of the speed required to escape Earth's gravity from a low orbit. Dawn built it gradually while carrying a relatively modest quantity of xenon. The same method becomes harder to scale for an interstellar journey. Ion engines require electricity. Dawn received that electricity from large solar panels. Sunlight weakens rapidly as a spacecraft moves outward. At Ceres, solar intensity is less than 1/7 of the level received near Earth. A probe traveling thousands of astronomical units would need nuclear reactors, beamed energy, or another powerful electrical source. High electrical power also produces waste heat. Space has no air to carry that heat away. Radiators must release it as infrared energy, adding area and mass to the spacecraft. Engine lifetime creates another constraint. Grids exposed to fast-moving ions gradually erode. Power processing equipment must survive years of operation. Propellant tanks still have a finite capacity, even when each kilogram is used efficiently. More advanced studies attempt to supply part of the power from outside the spacecraft. A distant laser or microwave beam could illuminate receivers aboard the vehicle and provide electricity for propulsion. Other concepts use large nuclear electric systems to operate engines with much higher power than Dawn carried. NASA-supported studies have examined characteristic speeds near 100 to 200 kilometers per second. Some were designed for travel to the solar gravitational lens region, beginning around 550 astronomical units from the Sun, with proposed flight times under 15 years. At 100 kilometers per second, the spacecraft would travel more than 5 times faster than Voyager 1. 1 light-year would still require approximately 2,998 years. A speed of 200 kilometers per second would reduce the crossing to about 1,499 years. The calendar improves by many thousands of years while remaining far beyond a human lifetime. Ion propulsion proves that a weak force can become powerful through patience. Its efficiency changes what spacecraft can accomplish within the solar system and may enable much faster probes into the surrounding interstellar region. Reaching 1 light-year within decades demands a far greater increase in available energy. During the 20th century, engineers began studying propulsion systems based on nuclear reactions, where each unit of fuel could release millions of times more energy than a chemical reaction. By the late 1950s, some engineers had already concluded that chemical propulsion would never produce a practical interstellar journey. The energy stored in chemical bonds was simply too limited. Burning hydrogen with oxygen can release enormous heat, but nuclear reactions operate on a much deeper part of matter. They change atomic nuclei, rather than rearranging electrons around them. That difference allows nuclear fuel to release millions of times more energy per kilogram than ordinary chemical propellant. Project Orion grew from that realization. The program began in 1958 and was led mainly through General Atomics in California, with support from United States government agencies. Its researchers included physicist Freeman Dyson and nuclear engineer Theodore Taylor. They studied spacecraft, far larger than any probe then being built. Some Orion concepts were intended for travel within the solar system. More ambitious versions explored journeys that would demand speeds measured as a noticeable fraction of light speed. The central idea used a sequence of external nuclear pulses behind the spacecraft. Each pulse would transfer energy to a broad rear structure, while a system of shock absorbers would spread the force before it reached the vehicle and payload. This approach promised an unusual combination. The pulses could provide much more thrust than an ion engine, while also releasing far more energy from each unit of fuel than a chemical rocket. A sufficiently large Orion vehicle could theoretically accelerate thousands of tons of equipment rather than a delicate payload weighing only a few kilograms. That scale was part of the attraction. An Orion spacecraft might carry heavy shielding, scientific laboratories, large antennas, or even human living space without sacrificing nearly all of its performance. Its proposed mass also created enormous engineering demands. The rear structure had to survive repeated bursts of heat, radiation, and mechanical force. Every pulse had to occur at the correct distance and time. The shock absorption system needed to smooth a series of violent impulses into acceleration that the spacecraft could tolerate. Materials suitable for thousands of repeated exposures had never been tested in the required conditions. Project Orion continued mainly until 1965. Several forces brought it to an end before any flight vehicle was developed. The Partial Test Ban Treaty of 1963 prohibited nuclear explosions in the atmosphere, underwater, and in outer space. Public concern about radioactive contamination was increasing. Government priorities shifted, and the program's political difficulty became as serious as its engineering difficulty. Orion remained a study rather than a spacecraft. Its calculations still changed the scale of interstellar planning. Chemical rockets suggested probes requiring many thousands of years. Nuclear pulse studies showed that much larger velocities could at least be examined with known physical laws. During the following decade, the British Interplanetary Society approached the same problem through fusion. Its Project Daedalus study ran from 1973 to 1978. The goal was to design an uncrewed probe capable of reaching Barnard's star within about 50 years. Barnard's star is a small red dwarf located almost 6 light-years from Earth. It was chosen partly because astronomers at the time believed it might possess planets, although those early claims were later rejected. The design work continued because the star still offered a clear test of whether a serious interstellar probe could be described using plausible physics. Daedalus was built on paper around pulsed fusion. Fusion combines light atomic nuclei and releases energy because the final nucleus has slightly less mass than the starting material. The missing mass appears as energy. This is the same broad process that powers stars, although a spacecraft engine would need to create and control the reaction artificially. The Daedalus concept used small fuel pellets containing forms of hydrogen and helium. Each pellet would undergo a brief fusion reaction, producing fast-moving charged particles. Magnetic fields would direct those particles backward to create thrust. The vehicle would operate in 2 main stages. A larger first stage would provide most of the acceleration before being discarded. A smaller second stage would continue accelerating the scientific payload toward its final cruise speed. The planned spacecraft was immense. Its total starting mass was roughly 54,000 tons. Around 50,000 tons consisted of propellant, giving the design a fuel fraction close to 92%. The scientific payload itself was estimated at several hundred tons. Even without a human crew, the probe resembled a traveling industrial facility more than a conventional spacecraft. Its fuel would have required collection, processing, storage, and loading on a scale never attempted for a space mission. Project Daedalus targeted a maximum speed above 12% of light speed. At that velocity, 1 light-year could be crossed in a little over 8 years of cruising. Barnard's star could be reached in roughly 50 years once acceleration and the full mission profile were included. The probe was designed for a flyby. It would pass through the target system at tremendous speed because the study did not include enough propulsion to slow the entire vehicle into orbit. Daedalus therefore improved the travel calendar by accepting a brief encounter after decades of preparation and flight. Its engine also depended on technology that still does not exist in operational form. Humanity has produced fusion reactions in laboratories and experimental machines, but sustained fusion power remains difficult to control. A spacecraft would need the reaction to occur reliably for years, while handling intense heat, radiation, magnetic forces, and a continuous flow of fuel. The machinery supplying those conditions would add mass. Radiators would be needed to release waste heat. Shielding would protect instruments from particles produced by the engine. Each solution would increase the energy required to accelerate the vehicle. Orion and Daedalus demonstrated what happens when interstellar propulsion gains a far denser energy source. The crossing time falls from millennia toward decades. The spacecraft grows until most of its mass exists to produce, contain, or survive the propulsion process. Both designs still carry the material that creates thrust. Their engines must accelerate that material from the beginning of the journey and discard it along the way. A different approach removes most of that burden. Instead of carrying the main energy source, a spacecraft can unfold a wide reflective surface and allow light arriving from elsewhere to push it forward. A spacecraft can gain momentum without carrying a conventional propellant tank. The pushing force can come from light itself. Light is made of particles called photons. Photons have no rest mass, yet they carry energy and momentum. When a photon strikes a surface and is absorbed, it transfers a tiny push. A reflected photon changes direction and transfers even more momentum to the surface. A solar sail uses that effect across a very large reflective sheet. The pressure from sunlight near Earth is extremely weak. A perfectly absorbing surface receives only a few millionths of a newton across each square meter. A highly reflective sail can receive nearly twice that force, because the photons reverse direction. The push would be impossible to feel with a hand. Across thousands of square meters, applied continuously for months, it can gradually change a spacecraft's orbit. The acceleration consumes no onboard propellant. As long as useful light reaches the sail, new photons keep arriving and transferring momentum. The sail therefore trades fuel mass for surface area. A successful design must be extremely thin. Every extra kilogram reduces the acceleration produced by the same amount of light. Engineers often describe this property through mass per unit area, meaning how much the sail and its supporting structure weigh for every square meter they cover. A large sail made from heavy material would receive a greater total force while gaining little speed because its mass would grow just as quickly. Useful sails require lightweight films, reflective coatings, compact deployment systems, and a structure able to hold the surface in the correct shape. That combination is difficult to build. A sheet only a few micrometers thick can tear, wrinkle, or fold onto itself. A micrometer is 1/1,000,000th of a meter. The material must survive launch vibrations while stored inside a small spacecraft. Once in space, booms or cables must unfold it without trapping a corner or creating a permanent crease. The sail must remain flat enough to reflect light in a predictable direction. Changing its angle allows the spacecraft to steer. Tilting the surface changes the direction of the reflected photons and therefore changes the direction of the force. NASA's Advanced Composite Solar Sail System was created to test part of this deployment problem. The spacecraft uses lightweight composite booms that unroll and extend outward. Composite materials combine different substances to produce useful properties such as strength with low mass. The booms support a square sail after deployment, demonstrating technology that could later be scaled for larger missions. Solar sails have already flown beyond laboratory tests. Japan's Ikaros spacecraft launched in May of 2010 with the Venus Climate Orbiter. Its square sail measured about 20 meters along each diagonal. The thin membrane deployed successfully in interplanetary space and used sunlight to alter the vehicle's motion. The mission confirmed that radiation pressure could provide measurable propulsion, while the sail's angle controlled the direction of travel. Sunlight becomes a weaker engine as the distance grows. Its intensity follows the inverse square relationship. At twice Earth's distance from the Sun, a sail receives 1/4 as much light. At 10 astronomical units, the available pressure falls to about 1/100th of the level near Earth. At 100 astronomical units, it is close to 1/10,000th. The sail keeps moving after the pressure becomes weak, but meaningful acceleration occurs mainly within the inner solar system. This encourages designs that begin very close to the Sun, where sunlight is far more intense. At 1/10th of Earth's orbital distance, the sail receives roughly 100 times the solar intensity experienced near Earth. The resulting pressure can produce much stronger acceleration. Reaching that region requires the spacecraft to reduce much of the sideways orbital speed inherited from Earth. A gravity assist, or an earlier propulsion stage, could direct it inward. After passing close to the Sun, the sail would turn into the proper orientation and use the intense radiation pressure to begin a rapid outward departure. Thermal survival becomes the central challenge. Near the Sun, ordinary plastics and coatings can soften, darken, or release gas. A darker patch absorbs more energy and heats further. The sail must reflect most incoming light while remaining stable across a surface that may span hundreds or thousands of square meters. Its supports, electronics, and payload also need protection from intense heat and charged particles. NASA Innovative Advanced Concepts Research has examined an extreme solar sail mission intended to reach approximately 500 astronomical units in less than 10 years. That distance is important because the Sun's gravity can focus light from distant objects along a line beginning around 550 astronomical units away. A telescope placed there could use the solar gravitational lens to study extremely distant targets with unusual magnification. Reaching the region within a decade would require an average outward rate near 50 astronomical units per year. Voyager 1 covers only a few astronomical units each year. An extreme sail could therefore cross the outer solar system far more quickly than any current spacecraft. The 1 light-year distance remains much larger. 1 light-year contains about 63,241 astronomical units. At a sustained average of 50 astronomical units per year, the crossing would require roughly 1,265 years. Acceleration near the Sun could create a revolutionary mission to the solar gravitational lens region, while leaving the interstellar calendar measured in more than a millennium. A solar sail receives its strongest push during the brief part of the journey when the light source is nearby. Farther out, the spacecraft coasts almost entirely on the speed it gained earlier. A concentrated beam sent from the solar system could continue delivering intense light long after ordinary sunlight had faded, allowing the same sail principle to reach a completely different range of velocity. The reflective sail can remain, while the source of light becomes an engineered machine. Instead of relying on sunlight that weakens with distance, a powerful laser array could focus energy onto the sail during the opening part of the journey. The laser stays near Earth. The spacecraft carries only the sail, a tiny payload, and the systems needed to survive the acceleration. This arrangement is called beamed propulsion. The energy source remains behind, so the vehicle does not need to accelerate a reactor, a large fuel supply, or heavy engines. Photons from the laser strike the reflective surface and transfer momentum. Each individual push is tiny. A concentrated beam containing immense power can deliver enough force to accelerate an extremely light spacecraft to a significant fraction of light speed. Breakthrough Starshot was announced in April of 2016 as a research program exploring this idea. Its long-term goal is a group of gram-scale spacecraft capable of traveling to Alpha Centauri. Alpha Centauri is the nearest star system to the Sun, located a little more than 4 light-years away. The published concept targets a cruise speed, near 20% of light speed. At that velocity, the journey to Alpha Centauri would take just over 20 years after acceleration. The proposed spacecraft is often described as a nanocraft. Its electronic package could weigh only a few grams. That small platform would need to contain a camera, sensors, a processor, a communication system, and a power supply. The package would be attached to a reflective sail several meters across. A sail that large can intercept far more laser light than the tiny electronics package could receive on its own. Its surface would need to be extremely light and almost perfectly reflective. Absorbing even a small fraction of a powerful beam could heat the material until it warped or failed. The laser system would also be far beyond any single instrument operating today. Starshot studies have described a phased array made from many individual laser emitters working together. A phased array controls the timing of its separate beams so they combine in the intended direction. The principle is similar to coordinating many small antennas until they behave like one much larger transmitter. For a laser system, the timing must remain precise enough for light waves from thousands or millions of emitters to reinforce one another. The resulting beam could reach a power approaching 100 gigawatts in some research concepts. 100 gigawatts is comparable to the electrical output of many large power stations operating at once. The array would need to direct that power toward a sail only a few meters wide while the craft rapidly moved away from Earth. Atmospheric turbulence can bend and blur light. An array built on the ground would require adaptive optics, using rapidly adjusted mirrors to correct the beam as it passes through moving air. A system placed in space would avoid the atmosphere while creating a much larger construction and maintenance challenge. Acceleration would occur over a relatively short distance. The nanocraft might reach its target speed within minutes, while traveling millions of kilometers from the laser array. During that period, the sail would experience acceleration thousands of times stronger than Earth's gravity. Ordinary spacecraft components could break under such forces. The electronics would need to be built as a compact, rigid package with very few delicate moving parts. The beam would also have to remain centered on the sail. A slight pointing error could allow part of the laser to miss, reducing acceleration or pushing unevenly across the reflective surface. The sail itself might need a curved shape that helps it remain inside the beam. Researchers have studied materials only a few atoms thick, along with microscopic patterns that control how light is reflected. Those patterns could improve stability while keeping the mass extremely low. Once the laser stopped, the craft would coast. At 20% of light speed, it would travel approximately 60,000 kilometers every second. The distance from Earth to the Moon would pass in a little more than 6 seconds. The average distance between Earth and the Sun would require around 42 minutes. One complete light year would take approximately 5 years. A nanocraft departing in 2026 could therefore cross the 1 light-year boundary near the year 2031. That calculation uses a simple cruise time. It does not include the years needed to construct the laser array, prepare the launch system, or test the sail. Acceleration also consumes time and distance, although both would be small compared with a 5-year cruise. The spacecraft would pass the boundary at full speed because the concept provides no equally powerful system waiting there to slow it down. For the title milestone, stopping is unnecessary. The craft only needs to cross the moving sphere 1 light-year from the Sun. For the first time in the journey, that event falls within a familiar part of the calendar. A person watching the launch could still be present when the crossing signal began its 1-year return to Earth. The first confirmation might arrive around 2032. The spacecraft would then continue outward through the estimated Oort Cloud at almost 60,000 kilometers per second. Reaching this speed requires an unusually small traveler. A gram-scale probe receives a large acceleration from a limited force because there is very little mass to move. Increasing the payload changes the entire design. A larger camera needs a larger power supply. More shielding adds material that the laser must accelerate. A stronger transmitter requires additional energy, cooling, and structure. Carrying a kilogram instead of a few grams could multiply the energy requirement hundreds of times. A vehicle large enough for people would increase the necessary beam power and sail area by many orders of magnitude. The 5-year answer, therefore, belongs to something closer to a flying computer chip than a traditional spacecraft. Its extreme speed comes directly from leaving almost everything behind. Crossing 1 light-year in 5 years becomes possible only after the traveler has been reduced to a few grams. That mass is comparable to a small coin or a thin electronic chip. The sail may span several meters, yet the working spacecraft attached to it would contain almost no room for conventional equipment. A gram-scale nanocraft might carry a miniature camera, simple sensors, a processor, a transmitter, and a tiny power source. Every component would need to survive extreme acceleration while using very little electricity. There would be no large telescope. Heavy radiation shielding would remain behind. Redundant computers, repair mechanisms, and powerful radio equipment would quickly raise the mass beyond the intended design. A conventional scientific spacecraft belongs to a completely different scale. Voyager 1 had a launch mass of approximately 825 kilograms. New Horizons weighed about 478 kilograms at launch. The Cassini spacecraft, sent to Saturn, began its journey with a mass of more than 5.5 tons, including propellant. Large observatories and planetary probes can carry mirrors, spectrometers, antennas, shielding, and several independent systems, because launch vehicles provide enough capacity to move tons into space. Accelerating that kind of mass to 20% of light speed requires vastly more energy. A crude interstellar vehicle would grow larger again. People need living volume, pressure vessels, water, food, air recycling, medical equipment, radiation protection, and a structure strong enough to contain everything. Even an unusually compact, crude design could weigh thousands of tons. A more heavily shielded vessel carrying supplies for years might reach hundreds of thousands or millions of tons. The difference matters because kinetic energy depends on mass. Kinetic energy is the energy an object possesses because it is moving. At the same speed, doubling the mass doubles the required energy. A 1-gram spacecraft and a 1-ton spacecraft differ in mass by a factor of 1 million. Ignoring losses in the laser, atmosphere, sail, and supporting equipment, the 1-ton vehicle would require 1 million times more kinetic energy to reach the same velocity. At 20% of light speed, even the gram-scale craft carries a remarkable amount of motion. Its kinetic energy would be around 2 trillion joules. That is roughly comparable to the energy released by several hundred tons of conventional explosive. A 1-ton spacecraft moving at the same speed would carry close to 2 quintillion joules. The beam supplying that energy would also lose part of its power through imperfect reflection and widening over distance. Breakthrough starshot studies have considered laser systems approaching 100 gigawatts. Such a beam would deliver energy at a rate comparable to the combined electrical output of many large power stations. The system would need to operate with extraordinary precision, while keeping its light centered on a sail only several meters wide. Adding mass would either reduce the acceleration or require a stronger beam, a longer acceleration distance, or a larger sail. Each option introduces additional engineering pressure. A wider sail becomes harder to keep flat. More laser power raises the temperature of the reflective material. A longer acceleration period allows the craft to move farther away while the beam spreads, making accurate focus increasingly difficult. Sail temperature may become the immediate limit. A material reflecting 99.99% of the incoming light still absorbs a small fraction. Under a beam carrying tens of gigawatts, that remaining fraction can represent millions of watts of heat. The sail must release absorbed energy as thermal radiation while maintaining its shape and reflective coating. A warped surface can redirect the beam unevenly and push the spacecraft away from the intended path. Acceleration forces create another sharp division between tiny probes and larger vehicles. A Starshot-style nanocraft may experience several thousand times Earth's surface gravity during the laser pulse. A solid electronic chip can potentially tolerate that force when designed without fragile joints or moving components. Large fuel tanks, human habitats, and broad scientific instruments would experience immense structural loads. Reducing the acceleration would protect the payload, while extending the time and distance over which the laser must remain focused. Communication becomes difficult after the acceleration ends. The small probe has only limited electrical power and a tiny transmitter. Its signal must travel across light years while spreading into space. Published concepts therefore require very large receiving systems on Earth, potentially combining many telescopes so their collected light can be analyzed together. The probe's laser signal would need to be separated from background stars and from the much brighter light of any nearby stellar system. At the 1 light-year boundary, communication is somewhat easier than it would be at Alpha Centauri. The nanocraft still has to point a narrow beam back toward a solar system whose apparent position changes during the flight. Available onboard power may come from a miniature, radioactive source, stored electrical energy, or light collected during the early mission. Shielding presents an equally severe mass problem. At 20% of light speed, even a tiny dust grain can strike with enormous energy. A thick frontal shield would protect the electronics while adding mass that the laser must accelerate. Designers have studied thin protective layers, narrow vehicle profiles, and large numbers of probes launched together. A fleet allows some craft to survive, even if others are lost. That approach suits a nanocraft mission, because producing many tiny units may be easier than protecting one heavy spacecraft against every possible impact. The title milestone creates one helpful simplification. The traveler only needs to cross the 1 light-year sphere. It can pass through at full speed without stopping. A spacecraft sent to rendezvous with a distant object would need to remove most of its velocity. Entering orbit around another star would demand a braking method capable of handling nearly the same scale of energy used during acceleration. A receiving laser, magnetic sail, stellar light maneuver, or onboard propulsion system might provide that deceleration. Each method adds equipment and mass. The 5-year crossing remains a credible physical target because its traveler carries almost nothing. As payload mass rises, energy demand, structural stress, and thermal difficulty rise with it. Velocity also enters a deeper regime where ordinary motion calculations gradually become inaccurate. Relativity shows that additional energy produces progressively smaller increases in speed as an object approaches the speed of light. Engine design can be set aside for a moment. The journey can instead be examined by giving the spacecraft a familiar acceleration and allowing that steady push to continue across the entire light year. A steady acceleration equal to Earth's surface gravity would feel familiar inside the spacecraft. Near Earth's surface, falling objects gain about 9.8 meters per second of speed during each second. A standing person feels weight because the ground prevents that fall and pushes upward with an equal force. Inside a spacecraft accelerating at the same rate, the floor would create a similar sensation. Travelers could stand, walk, sleep in beds, and pour liquids into containers while the engines continued pushing. The craft would begin slowly. After 1 second, its speed would be less than 10 meters per second. After 1 minute, it would be moving at roughly 588 meters per second. After 1 hour, the simple low-speed calculation gives more than 35,000 kilometers per hour. Continued acceleration would soon carry the vehicle beyond every speed reached by existing spacecraft. A chemical rocket cannot maintain that force for long. Its propellant would disappear rapidly, and the required energy would grow beyond any present power system. The calculation remains useful because it separates the distance from the machinery. It asks how long 1 light-year would take if a spacecraft somehow maintained 1 Earth gravity throughout the journey. The acceleration measured by people aboard is called proper acceleration. An accelerometer attached to the floor would continuously read 1 Earth gravity. The passengers would continue feeling the same steady weight, even as their speed relative to Earth became enormous. In the first scenario, the spacecraft accelerates across the entire light year. It makes no attempt to slow down at the boundary. According to observers on Earth, the crossing takes approximately 1.71 years. The people aboard experience about 1.29 years. At the instant of crossing, the craft is traveling at roughly 87% of light speed. That is about 261,000 kilometers per second. The spacecraft would continue gaining energy after reaching the boundary, although each additional increase in speed would become smaller. Special relativity governs motion at this scale. Albert Einstein described the underlying principles in 1905. One consequence is that an object with mass cannot be accelerated through the speed of light. As its velocity rises, the energy required for further acceleration grows increasingly large. The craft can approach light speed without reaching or exceeding it. This is what physicists mean when they say velocity approaches the limit asymptotically. The gap keeps shrinking while the limit remains unreachable. From inside the vehicle, the engine still produces the same proper acceleration. Travelers do not feel their acceleration fading. Earth observers measure the spacecraft's speed increasing more slowly as it approaches the speed of light. The two viewpoints agree once relativistic time and distance are included. Time aboard the craft also passes differently from time on Earth. This effect is called time dilation. A moving clock runs more slowly when compared with a clock in the frame from which its motion is measured. At ordinary speeds, the difference is far too small for people to notice. Atomic clocks can detect it aboard aircraft and satellites. At 87% of light speed, it becomes a major part of the journey. The travelers age by about 1.29 years, while Earth measures roughly 1.71 years between departure and crossing. Reaching the boundary at 87% of light speed leaves the spacecraft moving too quickly to remain there. A mission intended to arrive at rest could divide the journey into 2 equal parts. During the first half, the engines accelerate away from Earth at 1 Earth gravity. At the midpoint, the spacecraft turns around. Its engines then point toward the destination side of the journey and continue producing the same force. That second phase removes velocity instead of adding it. Passengers still feel pushed toward the floor because the craft maintains 1 Earth gravity in its own frame. The highest speed occurs near the midpoint. It reaches approximately 75% of light speed. According to clocks on Earth, the complete accelerate and decelerate journey takes about 2.21 years. The travelers experience approximately 1.89 years. At the end, the vehicle reaches the 1 light-year boundary, with its velocity reduced to 0 relative to the original starting frame. The additional stopping requirement lengthens the trip by only about half an Earth year in this idealized calculation. The result feels surprisingly short because continuous acceleration changes the early part of the journey so dramatically. Present spacecraft spend almost all of their flight time coasting at speeds measured in tens of kilometers per second. A 1-gravity vehicle keeps adding velocity through every hour and month. Relativity then reduces the amount of time experienced aboard as the craft moves faster. These numbers describe a thought experiment rather than a proposed vehicle. No known engine can accelerate a useful spacecraft at 1 Earth gravity for more than a year. The energy demand would be immense. Fuel or reaction mass would need to be supplied, unless energy arrived through an external beam or some other system. Waste heat would have to leave the craft through radiators. The structure would require protection from radiation and impacts. Even the no-stop journey reaches the boundary, carrying an extraordinary amount of kinetic energy. A collision or engine failure at that speed would allow very little time for correction. The calculation still reveals something important about the tidal distance. 1 light-year does not impose a journey lasting thousands of years through geometry alone. With sustained acceleration, the crossing can fit inside a small number of years. The barrier shifts into the machine, producing the force, supplying the energy, removing heat, and keeping the craft intact. At 3/4 of light speed or more, the thin material between stars no longer behaves like harmless, empty space. Hydrogen atoms, microscopic dust, and other particles strike the forward surface with energies transformed by the spacecraft's own motion. Voyager 1 moves through interstellar space at roughly 17 kilometers per second. At that speed, individual atoms and small dust particles strike the spacecraft with limited energy. Its aluminium structure and protective surfaces can endure the sparse environment for immense periods, even after the electronics fall silent. A probe traveling at 20% of light speed experiences the same material very differently. Its speed is approximately 60,000 kilometers per second. During a single second, it covers a distance greater than Earth's circumference. The space ahead may contain only a small number of particles within each cubic centimeter, yet the spacecraft encounters them at an extreme relative velocity. Most of the interstellar medium is hydrogen. Some hydrogen exists as neutral atoms containing 1 proton and 1 electron. Other regions contain ionized hydrogen, where the electron has been separated from the proton. Helium contributes a smaller share, along with traces of heavier elements such as carbon, oxygen, magnesium, and iron. At ordinary spacecraft speeds, these atoms create little immediate damage. At a substantial fraction of light speed, each atom arrives with enough kinetic energy to penetrate materials, break chemical bonds, and disturb electronics. The collision can strip electrons from nearby atoms inside the spacecraft's surface. That process is called ionization. A steady stream of fast impacts therefore behaves like a beam of particle radiation aimed directly at the front of the vehicle. The atoms themselves are microscopic. Their combined effect accumulates throughout the flight. Surface layers heat and erode. Crystal structures inside metals can develop defects. Electronic components may experience altered memory states or gradual damage to insulating materials. Sensitive equipment placed near the forward face would receive the greatest exposure. Interstellar dust creates a less frequent and more concentrated hazard. A dust grain may contain silicate minerals, carbon-rich material, frozen compounds, or fragments created during the formation and destruction of stars. Many grains are smaller than a human blood cell. Some reach dimensions measured in micrometers. At 20% of light speed, even a tiny grain carries its energy into a very small impact area. The collision can vaporize the grain and part of the shield. A brief cloud of hot plasma may form at the impact point. Repeated strikes can produce microscopic craters, remove surface material, and change the strength of the layers underneath. Researchers studying relativistic probes have estimated that gas and dust bombardment could damage or erode fractions of a millimeter to several millimeters of forward shielding during a journey to Alpha Centauri. The result depends strongly on the chosen material, the shape of the craft, and the assumed density of the interstellar medium. A path passing through a denser cloud would create more damage than one crossing an unusually thin region. The number of larger dust grains remains uncertain. Astronomers can measure broad properties of interstellar dust, from the way it absorbs and scatters starlight. Determining exactly how many dangerous grains lie along a narrow route between two stars is much harder. A sand-sized particle would carry far more energy than a microscopic grain. Its presence along any particular flight path cannot be predicted with complete confidence. Mission designs therefore rely on probabilities, observations of the route, and protection against a range of likely impacts. The simplest defense is geometry. A narrow spacecraft presents less frontal area to the incoming material. The sail used during laser acceleration could be folded, rotated, or separated after it had completed its task. The remaining electronics package could travel edge first, with its smallest surface facing forward. Sensitive systems would sit behind a dedicated shield. Sacrificial shielding provides another layer of protection. The forward material is allowed to erode during the journey while preserving the equipment behind it. Several thin layers can spread the energy from an impact and reduce the chance that debris reaches the main spacecraft. Different materials may serve different purposes. A hard outer layer can resist erosion. Lower density material can absorb expanding debris. Conductive layers can help carry electrical charge away from protected electronics. Each addition must survive the acceleration phase before it ever encounters interstellar dust. Redundancy offers protection at the mission level. A program could launch hundreds or thousands of nanocraft along slightly separated paths. Some might suffer damaged cameras or communication systems. Others could remain functional. The loss of individual probes would reduce the amount of returned data without necessarily ending the entire mission. This approach fits gram-scale vehicles more easily than a single large spacecraft containing irreplaceable equipment. Shielding has a direct cost in mass. One analysis of a 1-gram relativistic probe estimated that protective material could account for approximately 1 to 5% of the spacecraft's total mass. That amount sounds small until every fraction of a gram has already been assigned to the processor, transmitter, sensors, and power system. A thicker forward shield improves survival, while lowering acceleration from the same laser beam. Maintaining the target speed then requires more beam power or a longer period of illumination. A longer acceleration phase increases the distance over which the laser must remain focused. Stronger structures may be needed to connect the heavier shield to the sail. Those structures add mass of their own. A crewed vehicle would multiply the problem. Its frontal shield might need to protect a large habitat rather than a chip-sized payload. The propulsion system would have to accelerate the shield along with everything behind it. Reducing the travel time therefore changes the route itself. The sparse gas surrounding Voyager becomes an intense stream of energetic particles. Invisible dust becomes a source of gradual erosion and occasional concentrated impacts. A crossing that once seemed limited mainly by distance now depends on speed, acceleration, payload mass, shielding, navigation, communication, and the exact meaning of arrival. The spacecraft approaches a boundary that no camera can see. Nothing in the surrounding darkness marks the final kilometer. There is no physical shell at 1 light-year, only a calculated separation between the vehicle and the moving sun behind it. The arrival date depends entirely on what kind of traveler has been sent. A silent object drifting at Voyager 1's outward speed of approximately 17 kilometers per second would need about 17,635 years. A departure in 2026 would place the crossing near the year 19,661. The probe might remain physically intact. Its electrical systems, transmitter, and instruments would almost certainly have failed many thousands of years earlier unless they had been designed around forms of repair and power generation far beyond anything used today. Using Parker Solar Probe's momentary peak speed creates a very different calendar. If approximately 192 kilometers per second could somehow be redirected outward and maintained permanently, the journey would take about 1,560 years. The crossing would occur near the year 3,586. That result treats Parker's brief speed near perihelion as though it were a lasting interstellar cruise velocity, which its real orbit does not provide. A craft moving steadily at 100 kilometers per second would require approximately 2,998 years. Leaving in 2026 places its crossing near the year 5024. Doubling that cruise speed to 200 kilometers per second shortens the journey to about 1,499 years. The corresponding date becomes roughly the year 3525. These speeds would transform exploration of the outer solar system. They still leave 1 light year far beyond a human lifetime. Fractions of light speed change the calendar more sharply. At 0.1% of light speed, the traveler would move close to 300 kilometers per second. 1 light year would require 1,000 years, leading to a crossing near the year 3026. A speed equal to 1% of light speed reduces the voyage to 100 years. The spacecraft would reach the boundary near the year 2126. That century-long mission could connect generations of engineers, although no person present at an ordinary adult launch would be expected to witness the crossing. 10% of light speed brings the journey inside a decade. A vehicle departing in 2026 would cross near the year 2036. At 20% of light speed, the simple cruise time falls to 5 years. The boundary would be reached near the year 2031. This is the range proposed for gram-scale laser sail concepts. The date appears close because the traveler carries almost no mass, receives energy from a powerful external beam, and passes the boundary without slowing. A large scientific spacecraft at the same speed would demand vastly more energy. Adding thick shielding, powerful communications, long-lived equipment, or a human crew would increase the mass and change the entire propulsion problem. Continuous acceleration produces the shortest, idealized answers. A spacecraft maintaining 1 Earth gravity for the whole distance, with no attempt to stop, would cross after approximately 1.71 years, as measured from Earth. The people aboard would experience about 1.29 years because relativistic time dilation would become significant. Their speed at the boundary would be close to 87% of light speed. A journey designed to arrive at rest could accelerate through the first half of the distance, turn around, and decelerate through the second half. Earth would measure approximately 2.21 years. The travelers would experience around 1.89 years, and the peak speed would reach about 75% of light speed. Those figures describe what the laws of motion permit under a chosen acceleration. They do not supply the engine, energy source, shielding, radiators, or reaction mass required to build the vehicle. Each answer belongs to a different set of assumptions. The reference point decides where the distance is measured from. Cruise speed determines the largest part of the calendar. Acceleration time matters when the vehicle cannot reach its final speed immediately. Operational survival separates a working scientific probe from an inert piece of metal. Stopping adds another major energy requirement. Payload mass decides how much energy must be delivered. Relativity becomes necessary once the speed reaches a substantial fraction of light speed. The word "we" carries several possible meanings. It may describe a spacecraft humanity launched, even if no human travels aboard. It could mean an active probe, still collecting data at the crossing. A nanocraft weighing only a few grams produces the 5-year answer. A crewed ship creates a much larger engineering problem, while leaving the geometric distance unchanged. Even arrival has more than one meaning. Crossing the 1 light-year sphere does not guarantee that the spacecraft has escaped every part of the solar system. The distance equals approximately 63,241 astronomical units. Some estimates place the outer Oort Cloud near 100,000 astronomical units, or roughly 1.6 light-years from the Sun. The vehicle may therefore pass the tidal boundary while still moving among the most distant objects weakly held by solar gravity. Those objects would remain almost impossible to see. A nearby comet nucleus would appear only if chance carried the spacecraft unusually close to it. Across most of the route, the view ahead would contain stars against darkness. Earth and the Sun would lie almost along the same direction from so far away, separated by an angle too small for ordinary human vision to resolve. As the final seconds pass, instruments compare the spacecraft's estimated position with the calculated position of the Sun. The separation reaches 9.46 trillion kilometers. Nothing flashes. The engines do not respond. No field changes around the hull. A line inside the navigation computer records that the distance has reached 1 light-year. The spacecraft continues forward. Its confirmation signal spreads back through the region it has crossed, moving at the same speed that defined the milestone. 1 year later, the message reaches Earth. A machine launched in 2026 has finally traveled the distance light covers in a year.